Hello, people. Oh, wow. Look at that. 6 people in the meeting. That's great. Hello. How's everybody doing? I like that green screen.
One might liven it up a little bit. It is the afternoon.
Oh, nice pizza.
What are we drinking?
Hello.
It's not the Trump cocktail, is it? Clorox and hydroxychloroquine? Cure all your ills.
I spent a lot of time to think about how to illuminate my body from the inside.
Oh, well, yeah, well,
I mean,
won't get into that.
We could invert ourselves. I mean, that's supposed to be possible in 4 dimensions, right?
First he has to pull his head out of his ass before he gives advice, you know.
It require 4 dimensions to do that.
Unmuted.
Oh, hey, Marty.
No, you're talking about our president, I guess.
No,
Yeah.
no, we're talking about Andre Mirabelli.
No, I was thinking that you could shine through a fiber optic tube and swallow the fiber optic tube and get a UV light on the other end.
I find a small nuclear device will do the trick.
Yeah. Controlled explosion.
Clear that the virus is in the digestive tract.
Different virus. Oh man, we're in big trouble. Is entanglement entropy going to matter after we're all extinct?
Well, yeah, you wonder. Yeah, I mean, it's funny to be working on these problems because at first they seem pretty divorced from, you know, the political realities of our lives, but, you know.
Say that again.
It's a great escape.
Yeah, totally. And in the, you know, as the future continues to roll in, stuff.
Well, I believe in the block universe. There's no future and past. Everything is now.
Oh.
I'm just hoping we're in a multiverse and I can change channel at will.
Yeah. You know, there's a great cartoon, Rick and Morty, where it's all about the multiverse. I have to say, it's some of the best sci-fi writing on TV these days. Well, we got a whole bunch of people here, so let's get started. So today I wanted to take a little bit of a break from talking about the string diagrams that we've been using and just talk about entanglement more generally, except we're going to use a very specific example. Pretty much this entire time we're going to talk about what it means for just 2 qubits to be entangled. Qubits, very simple. We are building quantum computers out of them. They represent, you know, the quantum spin, a form of angular momentum of particles. I mean, it's, you know, generally a particle will have 2 kinds of angular momentum, orbital angular momentum and spin angular momentum. So we'll be talking about the spin one today and how we can interpret the entanglement between 2 qubits. And there's kind of like a beautiful geometrical way of thinking about it. And it's going to take us a little bit into some of the mathematics, kind of surprisingly, of special relativity. And so let's get started. So we begin with the sphere. Now, the sphere can be defined, by the way, if this is hard to see on my screen, like if I gotta make this a little bigger. Oh, and by the way, actually, before I even start, I forgot. I wanna emphasize this, which is that I made a cool website for all of the notes for these meetings. Yeah. So if you go to heyredhat.github.io, you'll get this page, and all the notebooks are up here. So today we're gonna be doing this one, spheres. And it's got this crazy kind of, this is like the back button. And so, you know.
Is that a selfie of you and your girlfriend?
What, oh, this? Yeah, we're in the sky together. We're just turning the crank. Well, so this image actually, I'm gonna come back to this.
That's a crank.
Yeah, totally. So I'm gonna come back to this image at the end of this meeting, because there's a kind of hilarious joke here to me, which is you look at this image and it's it's like a medieval image of, the angels turning the celestial spheres. But what I find funny about it is that there's two angels. Like you figure if, you just wanted an angel, turning an axis, you just need one of them to be turned to crank, but they put two in there. And we're going to think about that as a metaphor for something we're going to talk about today. So I'm going to come back to that later.
Is this an actual medieval
yeah,
drawing?
it is, yeah.
So this has some kind of religious significance to those who believe.
Well, right. So like the way I was looking at it is like, a lot of these religious symbols, crosses, spheres, threads, labyrinths, the whole panoply of like ancient poetic symbols, whether they appear in religions or ancient poetry or whatever. I mean, you don't have to accept a whole theology to be like, these symbols represent, something kind of fundamentally mysterious about the world. What's the deal with the fact that the stars seem to be like turning around this axis? And then, as we learn more about spheres, about axes, about how space works, time works, we can like overlay those perhaps ancient symbols with new meaning. So, I'm not necessarily making a religious statement, but
aren't there two angels because there are more than one sphere turning?
yeah, like in theory, right? Like in the standard kind of scheme, right? There were like a bunch of concentric spheres and then a kind of angelic intelligence which caused each one to turn. Now in this image, you're totally right. In this image, it seems like they're turning the crank of the same sphere, but then again, I don't actually know the full history of this image, so you might be right. Yeah. Like, to me, the joke, you'll see, is like kind of like, we're going to be working with the double cover of the rotation group, which is SU2. And you're going to think about like the double cover part, is like the fact that there's two angels. Okay, anyway, come back to that. So, if you want to follow along in these notes, they're here. And one great kind of coup is that if you click down here, launch binder, this will take a second to like load. It may have to rebuild this thing, in which case it'll take like 5 minutes to load, or it might take a minute to load, which is luckily the case we're in here. And it's gonna open up a Jupyter, notebook environment, like online, live, with all of the right packages installed, so that you can use the notebooks and do all the quantum calculations and see all the cool 3D graphics, just like literally in your browser. No setup involved. So that's nice. There's some documentation about that. So, okay, yeah, right. So now it's loading. It drops you in here. And, you can click on this. I recommend this tool, mybinder.org. It's great. Oh, I clicked the wrong one. Where is it? Spheres. And yeah, you know, if you shift click this guy, it'll after a second will run. True. Cool. But oh yeah, I'm gonna work locally for the rest of this meeting. But that is ready for you guys. Okay. Back to the sphere. Okay, so what's a sphere? Spheres are great. They pop up in a lot of different ways. Okay, so, you know, the classic equation for the sphere is r squared equals x squared plus y squared plus z squared. And x, y, and z are the coordinates in three-dimensional space, and r is the radius. And so if you take the square root of both sides of that equation, you know, you get that like the radius of the sphere is equal to the square root of x squared plus y squared plus z squared. But what is that? That's just the length of this arrow from the origin to the point x, y, z. And so this equation is true for all triples x, y, z that are at a constant radius from the origin in 3 dimensions, and that's a sphere. Now there's like lots of different, you know, higher dimensional spheres, you know, like a 1 sphere is like a circle, a 2 sphere is this one that we've been talking about, like a surface, a 3 sphere, et cetera, et cetera. We work with the 2 sphere today. Although the 3 sphere will come in, we won't dwell on that. Okay. But you know, we're too cool for just working with like standard Cartesian coordinates or whatever. So we're going to be representing points in our sphere using complex numbers. And this is a trick that, you know, if you've been to these meetups before, you're perhaps a little bit familiar with. The idea is we pick a north pole of the sphere, or a south pole, or some pole, some special point on the sphere. And then we do a stereographic projection from the sphere to the complex plane, which is taken to be an infinite plane cutting the sphere at its equator, or whatever is like at right angles to the point that you've chosen to project from. So you see there's this image here. We have a point M on the sphere. We've chosen P to be our pole. And then we have the complex plane coming in here, slicing that sphere at the equator. And if we follow a straight line from the pole that goes through this point on the sphere, it continues on and then hits the plane right there. And that's going to be our coordinate for that point on the sphere. Z equals x plus iy, where x and y now are the real and imaginary axes, you know, of the complex plane.
So, Matt, so if you do this in higher dimensions, let's say you did it in 1 higher dimension, then you'd need a plane with 1 higher dimension. So there'd be x and iy. Then what would be another one? Would it just be some arbitrary other basis vector that perpendicular to them, or does
something like that? Yeah,
have to be does something about I squared being -1 come into play here?
Right. So yeah, this generalizes to higher dimensions. You know, we won't go into it too much.
Can't you project any number of dimensions onto a flat plane?
Yeah, and it's like, you know, depending on, you know, if you're working in, you know, like
you won't get uniqueness, Michael. Just think of it.
Yeah. All right. Well, then you would project 4 dimensions onto 3.
That's right. And then the basis vectors, x hat, y hat, z hat,
yeah,
could not be 1 real and 1 complex. It'd have to be 3 different things. So the question is, why is I special here in the sense, or is it just picking out
the third dimension? The third dimension would just be another orthogonal dimension.
That's right.
Yeah, so it wouldn't form
then you have to be careful about multiplying these things, because when the I against the I gives you something in the X, whereas whatever your Z against your Z, what would that give you?
Well, you could call it J. You go I, J, K.
I understand. So what's J squared?
Then it's a quaternion.
No, that's 4. I think you need 4 for quaternion.
Right. So, you can have, 3 orthogonal vectors. What's special about the quaternions is that they form a division algebra, which means that you can divide them. And so they form scalars. You can think of them as just numbers. They can be added, multiplied, and divided. And that's true for real numbers, complex numbers, quaternions, and also octonions. So there's a whole interesting story there. Yeah, like you can do this sort of projection trick in different dimensions and in spaces of different signatures. It manifests a little differently. It would take us a little too far afield to go into the specifics of that. But so we'll see, right? So, but like I feel like the underlying question is, okay, like this plane, we're calling it the complex plane. Is there something particularly complex about it, or is it just a plane? Like, is this just a trick? Is this just a matter of description? Are we actually going to be using like the fact that like I is the square root of -1 in some particularly interesting way? And kind of like, in a way, yes, we'll see later on, why it's useful to use the complex numbers, and it'll come up in a little bit. Okay, so we have our pole P, we have our point M on the sphere, and we can project it to this point Z on the plane. And we get a different projection, if we chose a different axis or whatever. Now, this works for every single point on the sphere except for one, the point P itself. There's no more places on the sphere, on the plane to map that to. So we actually need more than just a plane. And so we think about this as we project the sphere to the complex plane plus infinity. And infinity is the point that the pole itself is mapped to. And so, if you think about it, it's like if you imagine like an infinitely small circle around the North Pole, that gets mapped to like the horizon. Like if you imagine living on the plane, there's like a kind of a circular horizon around you. And beyond every single one of those points lies the same point. And it's this point at infinity. And what is that? It's just saying like, suppose you're on a sphere and you use this sort of like coordinate system, then you'd have to describe in your coordinate system the point antipodal to you, the point on the opposite side of the sphere, as infinity in your coordinate system, okay? But here's the thing. This means that, unlike the case of where we're just using XYZ coordinates, oh wait, I got some kind of admit some people to this meeting, okay.
Matthew, did you just say you're identifying the two opposite poles?
No, I'm not identifying them. No.
But don't they both map to infinity?
No, the one pole just gets mapped to like 0, and the other one gets mapped to infinity.
It's really a hemisphere.
Well, so in this case, what happens is that, like if you think about the projection in reverse, like from the plane to the sphere, you'll see that points outside of the unit disk get mapped to the northern hemisphere, and points inside the unit disk get mapped to the southern hemisphere.
Oh.
Okay.
Oh, okay.
So here's the thing though, like suppose we have some function, and it's like a function of X, Y, and Z, okay? But now we want to like use the version of that function that's like in terms of complex, the complex plane plus infinity. We should be able to do that because there's no difference between them. Like X, Y, Z coordinate, complex number or infinity, it should represent the same thing. So if we have a function f of X, Y, Z, we want to instead use this f of, a complex number infinity version. But there's sort of like a problem there. Like everything's fine until like we have like this mathematical expression that the function is equal to, but like we can't plug infinity into it. So what do we do? Like how do we evaluate this function at infinity? And the answer is that we need two coordinate systems. We have to keep track of two coordinate charts. One's given by a projection, say from the North Pole, and one's given by a projection from the South Pole. And we have to keep track of both. And if we worry about, well, what's the function evaluated at infinity in terms of the North Pole, well, we could just switch to our coordinate system from the South Pole and evaluate that at 0. And similarly, we could get the value of the function with the projection from the South Pole at infinity by evaluating the function with the projection at the North Pole at 0. And really, you know, what this is sort of trying to say to you is like, as you move, if you were on the Riemann sphere and like your coordinate system was like one of these complex plus infinity coordinate systems, and your coordinate system, we imagine it moving around with you, then infinity is always going to be the point antipode, the point opposite on the sphere to you. And this infinity kind of like acts as your double with a coordinate chart of its own that shows you at infinity. Okay? Does that make sense? Incidentally, if you're wondering, you know, down here I have it like, so, you know, just the actual stereographic projection looks like this. You know, if you have your X, Y, Z points, the stereographic projection from the North Pole is just like, okay, if the Z coordinate is 1, then that goes to infinity. And otherwise, we get this complex number, X over 1 minus Z plus I times Y over 1 minus Z. And then if we wanted to do the South Pole projection, we would just flip the sign there. It'd be 1 plus Z in the denominators, just if you're wondering. So to summarize, you know, the familiar way of, well, I mean, so one initial motivation for doing this is like, you know, although using XYZ coordinates is great, it's actually, you know, not particularly spherical. Like we can describe like any point, you know, in 3D with the XYZ coordinates. And then we have to impose like, oh, we're just interested in the ones where like X squared plus Y squared plus Z squared equals 1, like the ones that are on the surface of the sphere. But, you know, what's kind of cool about this, like using complex numbers instead, is it's like we've imposed, there's like no redundancy. Like we've just like imposed, like these have to live on the surface of the sphere. So, okay, we're gonna come back to this notion of like, we need 2 coordinate charts in a little bit. And it's kind of related to this joke I'm making about the 2 angels, okay? Come back to that. All right, so now we have to talk about Mobius transformations. Throughout this, these notes, Mobius really should have an umlaut above the O, 2 dots, but I didn't put them in, okay.
And it's pronounced Mobius.
Mobius, yes.
Mobius.
Yeah, Mobius, great guy. You know, he's got his strip, he's got many things, but the Mobius transformations are great. Okay, so they're kind of like the kings of the complex numbers plus infinity world. So a Mobius transformation, you know, let me make this just a little bit bigger. Okay, that's better. So this is a Mobius transformation. It's like a little function. We plug in some Z, where Z can be a complex number or infinity, okay? And then the Mobius transformation itself is defined by like these 4 numbers, like A, B, C, and D. And there's just a very simple restriction on them, which is that AD minus BC can't be 0.
Ask a question.
Yeah?
So when you say you're explicitly including infinity, are you implying that you don't have to take limits to infinity? You can directly plug in infinity as a number itself?
Right, so great question, right? So what I'm saying is that if you want to evaluate this function at infinity, and you're working in the North Pole coordinate system, then to evaluate it at infinity, you switch over to using the South Pole coordinate system and evaluate it at the opposite point on the sphere.
So there's always a complementary, not infinite point.
Exactly,
Okay.
exactly. So when you take like, it's not about like limits or anything.
Right, okay, thanks.
So a Mobius transformation can be, you know, pretty much completely understood geometrically as a generalization of the stereographic projection itself. So before we just had like the sphere and then this plane cutting it, and we had some points on the plane, say, we projected them to the sphere. So, but like now we're gonna kind of generalize that. Like suppose you have some points on the plane, you project them to the sphere, but now you're allowed to like translate that sphere around in 3D. and then you're like allowed to like rotate it however you like. You can like, you know, pass it like below the plane, above the plane, rotate or whatever, who cares? And then at the end, you're gonna project all those points back to the plane. So here's like a sort of visual representation of it.
Matthew, is this Mobius equation just the way we designate rotational invariance, essentially?
Well, yes and no. So, okay, so as we'll see, it does.
That's a conformal transformation.
It's a conformal transformation, right?
Yeah.
So it's going to have the rotations, you know, X, Y, Z rotations and stuff, but it's also going to have something else. It's going to have boosts. Okay.
Have what?
It's going to have boosts. So we're going to talk about that in a second.
Okay. Lorentz boosts. Yeah.
Exactly.
Which are really mathematically they're rotations in the complex plane.
Kind of. Yeah. We'll in some ways the way I'm presenting it, it's going to be kind of the reverse. When we're going to represent them, it's actually going to be like. Well, actually, I'm going to come back to that point.
Well, where does that equation come from? Does it come from the matrix of rotation?
Yeah. We'll see that in a second. Yeah.
Okay.
Okie dokie. So these Mobius transformations are also known as conformal transformations. They're one-to-one. In other words, they map each point on the sphere to like a unique point on the sphere. They can deform distances, but they locally preserve angles. So this is the meaning of conformal. And so, you know, if you imagine the image being conformally transformed, all right angles are going to be preserved. All angles are going to be preserved. That means all circles are preserved. Mobius transformation takes circles to circles. But distances are potentially going to get fucked up. And, you know, the classic video, I have to say, this video has been on YouTube for years. And it's just great. Actually, I'm not going to make it full screen.
Among the most fundamental
Okay.
basic types.
Let's skip forward a little bit. Yeah, this is what they look like. Yeah. Ooh. So, I mean, these things were first discovered in the 19th century, you know. Look at that thing. Nice. Very cool. Mobius transformation. So there you go. Okay. So Mobius transformations are great. They kind of really make sense in this complex plus infinity world. They have a simple definition there. But as fun as it is to work with our complex plus infinity coordinates, it can be kind of awkward to keep track of that infinity. And so there's a trick, which is that we can work with a complex projective space instead. So I mentioned this, you know, to like in the first meetup at some point. So suppose we have a complex number or infinity. We can actually map it to a little complex 2 vector. Alpha and beta are 2 complex numbers. And the rule is basically like, suppose you have just a complex number z, it's not infinity. Then it gets mapped to this little guy with z in the first component and then 1 in the second component. And like in general, then you can like normalize that or whatever. And if, you know, the point's infinity, then instead you get that guy. And so you see already, this is like the representation of a qubit. In other words, that 1, 0 state represents the spin axis is pointed at the North Pole. It's like up. And so that's like when z is infinity. When z is 0, we get the basis vector 0, 1, which is the spin down state. And so this is a qubit. Like this is how you like geometrically interpret what a qubit is, okay?
Is that a typo? Shouldn't that be 0, 1, not Z1.
No, it's Z. So, you know, if you have some, so if you want to go in reverse, suppose you start with some alpha beta, then you can recover your Z coordinate by doing alpha over beta. So the original complex coordinate is the ratio between alpha and beta. And you see here, if we take Z over 1, that's just Z. What you may be noticing, however, is that there's a redundancy in this description. In other words, if I take this little guy here, this little qubit, alpha beta, and I multiply it by any complex number, it represents the same point on the sphere. So the point on the sphere is actually, you know, only encoded here up to a kind of redundancy. We can scale it, we can complex rotate it, and it gives us this. And so in quantum mechanics, like that, you can think about that as like relating to the overall phase of the wave function. We're not gonna talk about that right now. So we can trade our infinity for a second complex dimension. And now our XYZ point on the sphere is encoded in this two-dimensional complex projective vector, up to multiplication by any complex scalar. So you'll be pleased to know that we can upgrade our Mobius transformations in a very obvious way. We just take the little expression from before and we just A, B, C, D are now a matrix, a little 2 by 2 matrix, and the determinant has to be equal to 1. And these are called SL2C matrices. And this is a matrix group, and we've seen it before. It has 6 generators, and the 6 generators are just 2 copies of the 3 Pauli matrices, and the second set of 3 is multiplied by I. And what that means is that we can write any SL2C matrix as like this kind of expression. E to the a complex number times Pauli x plus a complex number times Pauli y plus some complex number times Pauli z. Now, if we only had complex components here, like say e to the b, ibx or whatever, then that would be a rotation around the x-axis. E to the I dy would be a rotation of d over 2 degrees, rotation of 3. You got it. Well, there's like a little thing where you got to use half angles. Let's not talk about that. E to the diy is like a y rotation. E to the fiz is a z rotation. And then if you drop the complex part, e to the ax is a boost in the x direction. E to the cy is a boost in the y direction, and so forth. And then if you allow, in general, both real parts and imaginary parts, then you get a combination of rotations and boosts.
Matthew, did you say X, Y, and Z are the Pauli matrices, or are they just...
Exactly. Yes, they are the Pauli matrices. Yes.
Okay.
Yeah, you got it. So, this is already starting to sound like relativity. We got some rotations, got some boosts. Hey, the Lorentz group, this is the Lorentz group. There's something very, very related to the Lorentz group, okay? Right. The difference between this and the Lorentz group itself has to do with the fact that we're using SU2 and not like SO3 or whatever, which has to do with the fact that, I don't want to get into it right now, basically, but it has to do with the fact that, like, for a fermion, you do a full 3D rotation and the wave function actually goes to the negative of itself, and then you have to do another 3D rotation to get it back. But that has to do with the overall phase of the qubit, which, as I said, we're ignoring because just the 3D point that's encoded in that qubit is defined up to multiplication by a scalar. So we're just going to completely ignore that for now. That's like a really important thing, but it's just not relevant to our story. It's basically just a technical detail. Okay. So now let's think about this in relativistic terms, like in the more classical relativistic terms, where we have 4 vectors, right? And so we look at our equation for a sphere. Like suppose we have a point on the unit sphere, right? It's going to be like 1, like the radius is 1 equals x squared plus y squared, plus z squared. But like we can arrange that into this form. 0 equals 1 minus x squared minus y squared minus z squared. And already that, you see you already get the signature of Minkowski space there. The time component or the first component is positive and the spatial components are negative. And so like, let's turn it into a 4 vector like this. We're say 1, x, y, z. And if we have a qubit, like we're working in a complex projective space, and if we're working with a qubit, we've taken the normalization of our state to just be 1, then we can get this vector just like this. So we get a t, x, y, z vector. The first component is the norm of the state. The second component is the expectation value of the Pauli x operator on that state. This next component is the expectation of Pauli y, and then the expectation value of Pauli z. And if this was normalized, then this will always be 1. And then we get, what I have here. And one can show that the 4 vector associated to a qubit that's transforming under some SL2C matrix, the 4 vector transforms under a Lorentz transformation. Now, what does that mean, though, mathematically? It means that it preserves this quantity, t squared minus x squared minus y squared minus z squared. Like if I have a 4 vector and I Lorentz transform it, like this better remain the same. T, y, x, and z can change, but this quantity has to remain invariant. And like that's what a Lorentz transformation means. So in special relativity, these are the transformations that take you between boosted and rotated reference frames. Rotations are obvious. Boosts, I guess, are less familiar in general, but they just mean now you're, moving at a different velocity. You like increased your velocity or decreased your velocity or something. So, the 4 vector, like if we're working in like Minkowski space, this could represent the position of a particle. It would be like t, x, y, z, like with reference to, a clock and an x, y, z coordinate frame. Or it could represent a momentum. And in that case, the first component would be energy, right? And then the other 3 components would be momentum in the x direction, momentum in the y direction, momentum in the z direction. So I've just said that's true, but we can actually kind of prove it.
That's for a massless particle. Where does mass come in here? What if you have a massive particle?
Yeah, great question. That's coming. That's coming right up. Don't worry. So the first thing to say is, check it out. Like, I can suppose I have a 4 vector t, x, y, z. I can form a Hermitian matrix. Remember, Hermitian matrix is equal to its own conjugate transpose. It has real, eigenvalues. It represents an operator, like an observable in quantum mechanics. It could also represent a density matrix, et cetera, et cetera, et cetera. We can turn any 4 vector into a Hermitian matrix using this following little trick. We just take the identity matrix, Pauli x, Pauli y, Pauli z, and it's like kind of multiply them by like the t coordinate, x coordinate, y coordinate, z coordinate. And you see, we just kind of stuff our t, x, y, z into this Hermitian matrix, and it ends up looking like that. And I can go in the reverse too. So like if I start with the matrix, I can take, the trace, after multiplying, with Pauli x or whatever and extract that component. So like here is some code that does it. We start with a random qubit. So 2 complex numbers, they're normalized. We convert it into a 4 vector. We go through the identity x, y, z, and we take the expectation value of that little state, given that operator. Then we convert that 4 vector into a Hermitian matrix, and we just multiply each of those components by the corresponding Pauli. And I alluded before that there's a factor of 1/2 here. So deal with that. You know, whatever, technical detail. Let's not dwell on it. But up to that, it works. So then we can go in reverse. We could just take that Hermitian matrix, take the expectation values with the Pauli's, and then check, hey, you know, do we get the same answer? Is this reversible? And so we check. We start with the qubit, get the 4-vector, convert a Hermitian matrix, and then go back to a 4-vector, and we ask, are those the same 4-vector? And the answer is yes. And furthermore, remember we just started with a qubit. There's actually a quicker way of just getting the Hermitian matrix that's associated to that qubit, which amounts to just taking the outer product of the qubit with a bra and a ket. In other words, if you have a qubit, you can form its density matrix. The density matrix is like the outer product of this guy with itself. Well, bra and the ket, so they're complex conjugated. And that's just the same thing you get there. So you can see that here. We take our qubit, we get the 4-vector, and then we get the Hermitian matrix. And then we see that H, the Hermitian matrix, is just the same as taking our original state and multiplying it and taking the outer product with its corresponding bra. Okay, does that sort of make sense? I mean, we can see these things. I don't know if this print, let's just do that, you know, why not? Seeing the fact that it's true is perhaps less exciting, you know? So, you know, okay, here's our state, you know. Here's the 4-vector. Here's the matrix, and then we're back to the 4-vector. Okay. So just a little proof of concept there. Okay, so, you know, we talked before about how, you know, you can transform states by like multiplying by them by linear operators. But if you want to transform a matrix, you got to act like on both sides to do like a basis transformation. So if we want to use our SL2C matrices to rotate and boost our Hermitian matrix, we got to act with the SL2 matrix, you know, on the one side, say on the left, and then with its conjugate transpose on the right. But what do we know about these SL2C matrices? Their determinant is equal to 1. Okay? Now what that means is that as linear transformations, they preserve the determinant of matrices they act on. If I have a matrix that has some determinant, and then I multiply it by a matrix whose determinant is 1, then the resulting matrix will have, you know, the same determinant as you started with. But now let's calculate the determinant of our 2x2 matrix. Here it is, you know, t plus z, t minus z, etc. So if you recall, taking the determinant means we take t for 2x2, t plus z times t minus z minus x minus iy times x plus iy. And then here's the thing, this is the thing I was waiting for, right? So here's where like the complex numbers, you know, do kind of make a difference, because when you multiply this out, you see that the determinant is just the Lorentz norm. So if we take a 4-vector, represent it as a Hermitian matrix in the way that I've been saying, using the Pauli matrices, then the determinant of that matrix is Lorentz norm. And because SL2C matrices preserve the determinant, they represent Lorentz transformations. So that's sort of the proof. Now, yeah, we were worrying about, what about like massive particles or whatever? And so here's a kind of a little like digression on that subject. It takes us, well, you know, yeah, it's an important part of the story. So suppose we have a qubit state. It's called psi. We can form its density matrix, which is Hermitian, with this little outer product guy. And it represents a pure state. And that means that its XYZ point lies on the sphere. T squared equals x squared plus y squared plus z squared. Or, you know, if we're thinking about this as like a momentum, E squared equals, you know, px squared plus py squared plus pc squared, etc. Okay, and if this is the unit sphere, then, you know, the t is going to be like 1. But, you know, let's just allow the state to have arbitrary norm. Then in general, we could say that, like, you know, quantum mechanics aside, in special relativity, you know, this represents the momentum of a massless particle. Because for a massless particle's momentum, it's like the relationship is like E squared minus px squared minus py squared minus pz squared equals m squared, the mass. And in this case, it's a massless particle, so m equals 0, and we get what we had before. E squared minus px squared minus py squared minus pz squared equals 0. So then we can interpret this in terms of special relativity. Again, nothing quantum mechanical here. We can interpret this in terms of special relativity as like a photon rushing in or out of like the sphere, like around you, you know, with a certain color. Because for a photon, you know, its frequency is proportional to its energy. And so we can think about these 4 vectors as being colored points on the sphere. The px, py, and pz parts give you the direction, and the E gives you the color. And there's a nice interpretation here, you know, which is that if you think about like the momentum as like an arrow from the center of the sphere to that point, and this point lies on the surface, you know, it's sort of saying that, like, you know, nothing can go faster than the speed of light, because it's like, as far as it can go, the point's like on the surface. But what if the particle does have mass? Then it has to travel slower than the speed of light. And in terms of our matrices, what this actually means is that the Hermitian matrix can't be written as a single outer product. Like before, we just took a qubit, and then we took its outer product, we found its like density matrix, and that represented a pure state. And what that means, it's a rank 1 matrix. But not all Hermitian matrices are like that. You also can have rank 2 matrices. What that means is it has to be written as a sum of 2 outer products. You have to have like, and you know, there's not necessarily one choice for this, but there's going to be some choice of, okay, we have like 1 density matrix, say 1 outer product of qubit, another qubit, and then some sum of these. And geometrically, this corresponds to a point in the interior of the sphere. So in this sort of like special relativity, momentum space interpretation of the sphere, massless particles live on the surface of the sphere because they're always going at the speed of light. But massive particles live in the interior of the sphere. Okay.
So Matthew, could you say that the surface of the sphere is the light cone, essentially?
Well, I would regard this as like, you know, it's like you're in some place, say, like in space. And you imagine like you're surrounded by this sphere of like all the photons, you know, coming in to your point, and all the photons, say, coming out. And so it doesn't necessarily represent, it's more like
the photons are bound to the surface.
Yeah, it's like,
they're going at the speed of light. The massive particles are within the light cone, if you're talking about light cones.
Well, I think you can think about it more like this sphere kind of like represents the intersection of your past and your future light cones.
The sphere is the intersection of the past and the future?
Yeah,
light cones?
I think that's a good way of thinking about it. So like at a given instant, some photons are coming in from your past light cone, and they're coming into your sphere, and they appear at a certain point, a certain direction and a certain color. And then maybe you're emitting some photons too. So they're coming out with a certain color and from a certain point.
But are the photons moving on the sphere, or only when they change frequency?
Yeah, so in this case, no, they're not moving. Like we're looking at the sphere as like, it's like a representation of an instantaneous moment in time. I mean, we're going to see a move, like I have an animation. But yeah, I mean, you should think about this like at an instant, photons coming in from a direction and they have a color.
So is this referring to a photon, or is this like, because you made it sound a moment ago like there are a whole lot of photons. Is this one photon being represented as?
Yeah, so in this sort of classical relativistic picture, you can think of each 4-vector as being a photon. So like one photon coming in from a direction in the color, then maybe you have another 4-vector that represents another photon coming in from a direction with a certain color, and so on.
Okay, and is this sum of the two operators, A psi and B, is that representing an ensemble of, like, how much stuff is included in that?
Yeah. So, okay. So when we talk about quantum mechanics, you know, yes, it represents kind of an ensemble. It's going to be a density matrix. In the relativity interpretation, it's just representing a massless particle. I mean, a massive particle. So, okay. So we're about to get into the part where it's like, I've called it like a tale of two spheres. Okay. Two spheres, two different interpretations. One is the sphere of like classical relativistic momenta. And then there's this like other interpretation of the sphere of a quantum mechanical spin. And the question is, how can we use these two spheres, these two interpretations of the sphere to kind of illuminate each other and come up with a cool way to visualize the entanglement between two qubits? So that's where we're going to.
Okay, this makes a whole lot more sense now that you said that, because
yeah.
I guess it's like showing stuff kind of familiar from quantum mechanics, but speaking all the time about special relativity.
Exactly. Yeah. You bet.
Matt, can I ask a question? You seem to show that a massive particle is written as a sum. Is this should this be interpreted as a superposition, or am I?
It's more like a classical. So in quantum mechanics, this would be like a classical sum. You know, it would represent classical statistical uncertainty about what state it is.
So it's not a superposition of states.
Yeah, it's not a superposition. It's like A and B would be like the probabilities, and they would have to sum to 1 in a density matrix. I'm about to come to that. You can think about this like, you know, the difference between rank 1 and rank 2 is like, suppose you took the matrix and you did the SVD, like you did a singular value decomposition. And the question is, how many, you know, singular values are there? And if you know, do the decomposition for rank 1 matrix, there's just going to be 1 singular value. And if you do it for rank 2, there's going to be 2. And that's the difference.
And why does a massless particle have only 1 value again?
Yeah. Okay. So
Why
I'm
is
about to come to that. Yeah. Or like why we like doing that. Yeah. I'm gonna go into that. Okay. So when we're talking about quantum mechanics, you know, a Hermitian matrix, like we've been talking about, represents a general mixed state density matrix. Now, technically speaking, the rule for density matrices is that, you know, their eigenvalues are positive and they sum to 1. So, you know, traditionally quantum mechanics, it's like you form the density matrix, and then in that basis, the probabilities of the different outcomes are like along the diagonal of that matrix. And for, you know, density matrices, if you take the expectation values of the XYZ operators, you know, if the qubits were separable, these points, the 2 points, we have 2 qubits. We take their XYZ expectation values and they're separable, the points will live on the surface of the 2 spheres, and if they're entangled, then the points will lie in the interior of the sphere. Until finally, like if you had like a mixed state where the point's totally in the center of the sphere, like that's the maximally mixed state.
But why does that represent a massive particle?
Yeah, totally, right. So again, there's like a story of 2 spheres, 2 different interpretations that I'm gonna try to, you know, allow to collide.
Is there a point you're waiting for where you expect a lot of synthesis to happen, where people will be like, oh, okay, and we should like
it's coming up. It's coming
wait
up.
till that happens to
Totally, yeah.
Okay.
But you say a massive particle is a mixed state, whereas a massless is a pure state?
Yeah, that is what I'm saying. Like,
Is that-
it's
is that-
kind of an analogy.
Is that
but it's kind of a
standard?
precise mathematical
Is
analogy.
that standard quantum physics? I mean, is that
No.
the interpretation? I don't know.
Well, I mean, yes. You know, both of these things are standard in relativity and then like also in quantum mechanics. The connection between the two, you know, has been written about a lot. It's like
So an electron is a mixed state. A photon is a pure state. An electron is mixed state.
no. See, because that's mixing the metaphor.
Okay.
Yeah, totally. So yeah, to emphasize it again, it's like on the one hand we have the relativistic geometry of momentum space, which is like kind of cool. Like it's the space we actually see around us, the so-called celestial sphere, the sphere of like all the points of light. I mean, it's nice to think about like you're out in space or whatever, and you see a bunch of constellations. Those are like, you know, they're in a direction and the star has a certain color. But of course, we're not talking about stars. Literally, we're talking about the photons coming into your eyeball. And on the other hand, we have the quantum geometry of a qubit, a little spin half particle. And basically what we're going to do is use the fact that it's easy to visualize, you know, special relativity to visualize the quantum case. And now here, this little paragraph here is going to go into a little bit of a sidebar, but go into kind of like some of the reasoning for the relativistic geometry picture. And this is very quick, but this, you know, may help you guys understand. So again, this has nothing to do with quantum mechanics per se.
Would you say it's true that in quantum, as far as quantum mechanics is concerned, like, you know, boring sort of not spinner, just like not Dirac, but Schrodinger, that it makes no distinction. It doesn't privilege a photon over an electron. Particles are particles, or whatever. Like all things that you can look at and do experiments on are basically treated equally. Not in every way, but like you have to know, okay, this is a 3-state thing, that's a 2, whatever. But like the mass, no mass, as long as you speak in terms of like its momentum, it doesn't really.
Well,
quantum mechanics doesn't make you think a lot about the electrons that turn up in interaction terms.
Sure.
But I guess they're sort of a.
So, you know, you
there's
can.
more to symmetry. Special relativity seems to break that symmetry a lot.
Right. So I guess I would say it's like you can just work with 4 vectors and then, you know, okay, so this 4 vector, you know, represents a massive particle or a massless one.
Yeah.
Now there's a trick that I'm about to say that allows you to use the whole Hermitian matrix thing to very cleverly represent the little groups of particles. So this is like terminology from, you know, relativity. The little group of a particle is basically its spin. The idea being that like a relativistic particle has both like a momentum, you know, and a spin, and they're kind of independent of each other. Like I can change the momentum without changing the spin and vice versa. And, you know, if you go read the article about, you know, Wigner's classification of, you know, the elementary particles in terms of mass and spin, you know, the great way to do that is by analyzing like what are the little groups of particles, and they're different for massive and massless, okay? And, you know, we can actually kind of read this off of this little formalism that we're using here. So this is like kind of one reason why this formalism is useful. So for a massless particle, its Hermitian matrix can be expressed as an outer product of a bra and a ket. But if you think about it, like suppose we just had the bra and the ket. We're going to combine them eventually into a Hermitian matrix. But the thing is, each of them is only defined up to an overall complex phase. Like I was saying before, we could multiply each one of them by any complex number, and it wouldn't change the XYZ coordinate they represent. Now, suppose we have that bra and the ket, and we multiply this one, you know, we complex phase this one like a little bit in this direction, and then we complex phase the other guy in the opposite direction. And when we multiply them together, they're going to cancel out. And they're going to give the same Hermitian matrix as before. So we could have a 4 vector. We could represent as a Hermitian matrix, and then we could break it down into a bra and a ket. But the thing is, now there's a redundancy. We can, multiply the one guy by a complex number and the other guy by the inverse of that complex number. And it's going to give us the same Hermitian matrix. And we're going to think about that as representing the little group of a massless particle. The little group represents the polarization of a photon. Now, what does a photon do? A photon always moves at the speed of light in some direction, but it's corkscrewing around in the plane orthogonal to its motion. So classically, like, this is how photons work. Like, they come in, like, they corkscrew, right? And the frequency has to do with, like, how fast it's corkscrewing, okay? And, you can keep track of where it is in its little corkscrewing by giving a point on a circle. And that can be given by a complex number. So we could say that, a massless particle has a corresponding Hermitian matrix. And so it's defined by this, like, bra and a ket that we combine, but that Hermitian matrix is only defined up to this, like, arbitrary phasing between the two parts. And that gives you the little group of the massless particle. It's just U1, the circle group. We can rotate the polarization of a photon without changing its momentum and vice versa. Similarly, if we have a massive particle, we break its Hermitian matrix down into 4 parts, the sum of 2 outer products. And you could wonder, like, is there something that we can do to those guys, like, similarly, that, like, we do, like, this to one guy and this to the other guy and then combine them, and then it doesn't change the Hermitian matrix they represent? And it turns out there is, and it's SU2. It's the rotation group. And therefore, the little group of a massive particle is SU2. In other words, massless particles have polarizations and massive particles have spins. And I won't go into
does what you said about massless particles, in addition to photons, would it also apply to gravitons, spin 2?
Yeah, the argument does not fail. And in fact, there's a whole interesting story about how you can use exactly this formalism to represent higher spin particles. So right now, we're just working with, like, spin half particles, basically. Or, well, I guess that's not actually the most precise way of saying it. But yes, you can totally represent, like, a graviton as spin 2, right? So, we can, there's a thing you can do. I don't want to go into it right now, but essentially, well, yeah, we'll talk about it in a couple weeks, but I mean, the upshot is something like, you can represent a spin half state as, like, a point on a sphere, and you can represent a spin 2 state as actually 4 points on a sphere. It's okay if that makes no sense. It's kind of weird. We're going to talk about it later, unfortunately.
And then another question, maybe I'm just jumping the gun, but bosons that mediate the weak force are massive, and yet they are spin 1. They're not half spin.
That's fine.
So what you're saying would still apply, the same rules would apply massive or massless.
And again, remember, this isn't really quantum mechanics.
Yeah.
This is really just kind of a funny way of talking about classical relativity that somehow uses exactly the same mathematical structures that you use when we talk about.
But but of course, the big thing now in physics is to merge relativity, with quantum mechanics.
That's why we do it. Yeah.
So I'm just curious if in fact you have massive bosons, and I guess the ones that mediate the weak force are the only ones I'm aware of. They have spin 1. So would this mathematics apply to them, even though
Yeah, so if you
They're
had
massive.
a massive particle, you could think kind of like, you know, like suppose it was spin 1. You could sort of have just like 2 copies of this construction. It's like a spin 1 particle, you could sort of think about it like 2 points on a sphere. And so you would sort of like repeat the construction for each of those 2 points, treating almost like the spin 1 as being built out of 2 spin half particles. There's a beautiful story about that. It's called like the Majorana stellar representation or whatever.
Of course, the reason
Talk about that later.
the W and Z bosons have mass is because of symmetry breaking, which is a whole other thing. I mean, that you could say they started out as massless, and by symmetry breaking, they acquired mass.
Totally, yeah, and that's a whole interesting story. I wish I could, you know, bring.
Yeah, I mean that's a whole other issue. Yeah,
Totally.
I can see. I mean, basically, we're talking about relativity here.
Yeah.
Yeah.
We're keeping it pretty much.
Can I ask, what is, I've never seen this. This is really cool. I've never seen mass or masslessness be the source of SU2 versus U1.
Yeah, and that,
You know, or like that where mass imposes that you need these rank 2 things, which has this little group, and
yeah.
no mass is rank 1. So what, like historically, when did this become like a way of looking at it that was popular?
Yeah, there's a long and complicated story. I would say this account of it, I picked up from, you know, one of the great physicists, Nima Arkani Hamed. He has a great lecture, and there they go under the name spinor helicity variables.
Okay, so it's pretty recent, and it's not in the curriculum of like,
yeah,
traditional way you talk about
sure.
physics.
Yeah, I mean basically, because again, the thing is, I keep emphasizing like this is classical relativity, because like over here, like you know, I had the thing where it represents, all right, here an SL2C matrix is given by this. Now, like think about the boosts. Like a boost in the x direction would be like e to the ax. There's no imaginary component there, which means that does not preserve the norm of the vector. In other words, this is a representation of SL2C of like a Lorentz group, but it is not unitary. It is not a unitary representation. When you actually do quantum field theory, you have to use unitary representations of the Lorentz group. And the unitary representations of the Lorentz group are infinite dimensional. And so you use like a sort of grander framework than what we're doing here. So, you know, these things come up in like quantum field theory, but not to represent the quantum states. The quantum states themselves use a completely different representation of SL2C. Now, the whole thing is that like SU2 is a compact group. It's the rotation group, it's compact. And one consequence of that is that its representations are finite dimensional. And that's why we can represent a qubit as just like 2 numbers, a little vector of like 2 components, or a spin 1 could just be like a little 3 component vector or whatever. But we're not just thinking about SU2, we're also thinking about SL2C. When we add those boosts in, they don't preserve norm. It's not a unitary representation, and therefore it is insufficient for doing quantum mechanics. To do real quantum mechanics with the Lorentz group, you need to use an infinite dimensional representation. And that is kind of why quantum field theory is often really hard, because it's like an infinite number of dimensions, man, you know? Anyway, so that's a cool story. We won't go too much into it because, again, really we're just delving into this relativity stuff. I mean, it's really cool, but also, you know, our ultimate goal is to understand the entanglement between 2 qubits. So that's what we're gonna go to in a second. So, all right, well, so here's a little visualization, a little break. Like, let's look at some Mobius transformations, like just for the sake of it, right? Now we're gonna run this like a bunch of times, and you know, I'm gonna adjust the rate of the simulation and stuff, and like, because this is quite slow, but I just wanna start off slow, so you see. So what I do here is I create a bunch of random points on the sphere, okay? And they're initially like little two-dimensional complex vectors work in the projective space. You see, I create these points as just like little spinners or whatever, but I don't care about their normalization. In fact, they're definitely not normalized. Then I construct a random Mobius transformation. How do you do that? Well, I just generate 6 random numbers, and I form 3 complex numbers out of them. And then I weight the 3 Pauli matrices by those 3 complex numbers and take the matrix exponential. And, is it in fact a Mobius transformation? Well, we can tell if we look at its determinant, and the determinant is 1. Well, it's 0.999999999, but let's say 1. Then we draw a sphere. We draw the points on the sphere, and then we, each time step, Mobius transform them a little bit. So what we're doing is we're taking a Mobius transformation, and it's kind of a tiny Mobius transformation. That's what this DT is here. So it's like, it's not gonna push it very much, and then we're gonna repeat it. So this is like, we're watching, kind of like a repeated Mobius transformation. Okay.
Matt, when you do that, do you use the same 6 randomly chosen numbers, or do you at every instant?
Yeah,
choose
each time it's different. Yeah, each time it's a different
you pick 6 random numbers and you move them a little, and then you pick 6 different random numbers and move them a little again.
Oh, sorry, I misunderstood. Each time I run this program, it chooses new points at random and a new Mobius transformation at random. But no, each moment in time, it's applying the same Mobius transformation again and again and again. Let me get out of the notebook. Sometimes the notebook craps out, as we all know. Test. Okay. Oh, that's fine. Okay, so the points have colors, and I mean those colors kind of like quite literally. And they're moving, and so this motion, it's not necessarily visually obvious because it's running so slowly. This motion is a combination of a rotation and also some boost, and it's preserving the angles between the points. Let's speed it up a little bit because it's sort of painfully slow. Whoa, look at that. Yeah. Warp speed. Yeah, so they're getting blue shifted. So again, this is cool because, this is like what you would see if you were in your spaceship or whatever. This is what they tell us, right? You were in your spaceship and you were like, zipping along, and you like rapidly were like increasing your velocity. You were like in the process of boosting higher and higher and higher and higher and higher velocity, and like maybe also like rotating around at the same time. You would see like the image of the world around you distorted in this way. And you would see, if you were moving at the speed of light, like as you get closer and closer to the speed of light, like all of the photons would appear to be getting like pushed and in the direction of your motion and getting blue shifted. Do it again. So, each one of these, again, is random. I mean, you can tell some of them are more boosty, other ones are more rotation-y, and pretty much no matter what color they start out with, they end up blue. I mean,
Is it somewhat of an approximation to be talking about effectively accelerations in special relativity, but like as a sequence of
Yeah,
a
well, that's
lot
what I
of
mean.
boots
It's
one
like,
after another?
so, you know, I have a tiny Mobius transformation that like rotates a little bit and like boosts it a little bit. And then I apply it over and over and over and over again. And so that's like an acceleration. You see what I mean? It's like I keep increasing velocity.
That's how it seems. I was always made to think that acceleration is the big thing missing from special relativity. So how accurate you are when you talk about rapidly sequence boosts, I wonder. Never thought of that before.
Yeah, no, it's a great question. Because the thing about it is like, the simplification is, of course, if I'm in space, okay, depending on my rotation and my velocity, my photons will be Mobius transformed. But of course, if I'm actually moving at some velocity or whatever, I'm moving in space, right? And so I actually would see different things. What this represents is a kind of hypothetical thing. It's saying like, suppose you fixed exactly where you are in space and time. And then you imagined taking different perspectives from that particular place, but suppose you were rotated. Suppose you were passing through that point and you were moving at this velocity, or you were passing through that point and moving.
Right, so you have a million observers everywhere and you take a snapshot of everyone's view and then you're playing it like one observer to the next observer, you know, you're sort of.
Well, in this case, it's like from the perspective of one particular vantage point seen from different angles and as if you were moving through that point at different velocities.
Right,
So,
like if a bunch of different people were moving at different velocities and all sort of intersected at one moment, you know, and each one has a different velocity. There's sort of this take a cross section of all those perspectives.
yes, yeah, sure. That makes sense.
So what is the direction that they all end up coming in from? So they all end up coming in from the same single direction.
So so that direction is like ultimately the direction that this particle is moving in. So that's like its velocity.
Does it come in from behind you or from in front of you?
So these stars get boosted in the direction of your motion. So like, yeah, wherever they end up, like that's kind of like the direction that the velocity vectors point.
If I'm going forward in my spaceship, I end up seeing in the end all light coming in through the front.
Yeah, totally. Yeah, it's super weird. Yeah, and like if you were a photon, yeah, it would be like the entire universe would be kind of just a point of light in the distance right in front of you.
So not from behind, but from in front.
Not from behind. I think that's right. Huh, you know, it's like, I haven't seen it myself. Like, yeah, I think that's right. So, you know, people classify the different Mobius transformations in different ways in terms of like terms like, are they elliptic, parabolic? And they just basically have to do with like, you know, to what extent is it rotation-y? To what extent is it boosting and stuff? But you see, you know, they have this sort of character. You can kind of tell that they're conformal, I guess. Look at that go. And yeah, so I mean, I had to do a little trickiness to do the color. Like basically, like if the energy of the photon gets too high, I just like cap it at a certain value, which is just blue. So anything like over a certain energy, I'm just like, that's blue. And anything like, you know, and then red is the lowest energy. Okay. So there's that. So that's relativity. Okay, so now we're getting into the real stuff. So this is kind of the punchline. We're coming in for a landing here. All right. Suppose we have two entangled qubits. Like now, you know, forget about momentum for a second, relativistic momentum. Think about qubits again. We have two entangled qubits, A and B, and we want to visualize their entanglement. So how could we do that? One thing we could do is this. We could go through all the points on the surface of A's sphere. which correspond to all of A's pure states. Like these are all the states that like A could be in. It's a qubit. Its states are given by these, you know, points on a sphere. Those are the pure states. And we could form the projectors onto those points. We could just take, to do that, you know, if you just have a, you know, if this qubit represents the point that you want to project onto, then you can just form the projector like that. It's just like the density matrix. So we get all these projectors. So these are all the states A might end up in due to some measurement on A. And then we're interested in is how, quote unquote, B is steered due to that projection. And because of the entanglement, when A ends up in a certain state, it's going to be like some linear map has been applied to B. And we're going to be thinking about entanglement like a map from A to B and vice versa. We form all possible projectors corresponding to points on the sphere. We tensor them with the identity, so they only act on A. And then we project the entangled state using each projector in turn. And due to the entanglement, B will be steered to a certain state in each instance. And furthermore, B's state will be weighted by the probability of that outcome for A. So to visualize this, we're going to pepper A's sphere with points, each with a color unique to its location. We're then going to project A into each of those states in turn and see where B is projected to. And then we're going to take B's XYZ expectation values and place a point there, which is the same color as the point on A's sphere.
And Matt, we're talking about maximally entangled states.
Well, we're going to see it in all three cases: maximally entangled, separable, and the middle, whatever. Oops.
And could this also be for more than two particles?
Oh yes.
If they're not, because unless they're maximally tangled, you could have multiple particles that are entangled.
Yeah, we're going to talk about that a little bit. This the exact kind of thing that I'm going to show you is something that sort of is perhaps a little bit special to the 2-qubit case, but it does generalize. Okay. So here it is. Here's A, and here's B, okay? And then I got all these points on A's sphere, and I've given them a color, which is just like its XYZ location, like as a color, okay? So they're color-coded based on where they are on A's sphere. And then we go through each of those points. Like I take that little point, like this one here, and I form its projector, and I project A into that state. And then I go look at like, oh, what happens to B? And it turns out like, okay, so that's that green guy here. Well, it looks like that guy gets steered over here to this point. And so every point on A's sphere gets mapped to some point over here. Let's run it again. We're gonna do this like a bunch of times. Oh, interesting. There's that. What's going on there? Let's do another one. Okay. So some observation, you know, one observation you can make is it looks like that we always get like some kind of ellipsoid. Sometimes it's like a sphere-ish looking thing. Another time it was like sort of just like a line. And
I'm sorry, I'm losing the thread here. Can you say again what exactly so you're saying that what are the different, if particle A is on the left, what are the different dots on that sphere, the different possible positions of particle A?
The different, so, okay.
What does that represent physically? The different possible
Those are all the possible states of A. It doesn't really have to do with the position of the particle in space. They're all its different spin states.
They're
like
all different spin states. So each one of those each colored dot on that sphere is a direction for the spin
Exactly.
of particle A. So, okay, if that's the direction for the spin of particle A, and then what's the other sphere?
The other sphere is I go through each of the points on A's sphere, and I project the entangled state, the A part of it, into that state. So I project A into, say, the state corresponding to this green guy, and I project A into the state corresponding to this yellow guy and this red guy, and all of these points.
You're saying, so now you're saying I have a particle A in a certain state, and I measure its spin in some other direction, not collinear with its state.
Yeah, I mean, it could be collinear, it might not be. It's just saying I'm going to consider all of its states.
Right.
And I want to know for all of the states of A, what state does B end up in?
Slow down, you just lost me. There's two separate possibilities here. Am I thinking there's one state of A and I'm projecting it onto different possible directions?
No. It's like,
Matt, aren't we talking about two particles?
Yeah, is there a particle B here? I think that's what
The blue is particle A and the pink is particle B, right? Two particles.
so we have a two-particle state, A and B.
Right.
And then I'm gonna,
So I'm just trying to get what one point on particle A represents, on the blue sphere represents. Does it represent the place I'm going to measure it, the direction I'm going to measure it in, or the direction its state is in?
the direction that you're gonna measure it in. So
it is in a certain direction, a unique direction, and the different points represent what direction I'm going to measure that unique state in.
Andre, it's a spin state.
Yeah, it's a spin state, and the dots are what? Different.
They're different spin states. They could be any direction.
Are these
Different spin states, and they map particle B to another specific spin state.
I got to go slower than this.
Yeah,
Let's talk about particle A for a second. Particle A has a spin in a certain direction, and the dots, the green, blue, and red dots, are directions I'm going to measure its spin in. Is that correct?
Yeah, so if you look here, there's actually this arrow inside that sphere.
Right, that's the spin.
That represents like the expected value of its spin axis.
Right. Right.
And then I just want to consider though, like all the possible states of A. And, you know, in general, like that would be like the entire surface of the sphere, but I've done like a simplification and I've just used a finite number of points and I've given them all color here, right?
You could have an infinite number of states.
Matt, you're again.
Every point on the sphere is a state of a qubit.
You're again confusing me. There's a difference. That arrow is one state, and I could measure for that one state its projection on any direction.
Yeah.
Then there's a different question.
Mm-hmm.
Each direction that arrow could have been in a different direction, and then I could have measured it in some other direction. So I'm just trying to get the difference between.
So it's like
between what direction the state is in and what direction I'm measuring it in. And the way I'm interpreting you is the arrow is what direction the state is in, and those colored dots are what direction I want to measure that state, that previous state in.
You're like 90% right. So you're completely right that the arrow represents, the expected XYZ value, like the state of A. These colored dots don't necessarily represent like you're measuring along that direction. We're actually like leaving open like what measurement you do. All we're saying is, suppose you did a measurement and you got a certain outcome, and the outcome was like the state of A was, say, right here with this blue dot.
So then it's different arrows. So that would make a different arrow.
Yeah, so like we just think about, okay, suppose the measurement takes place. We're not gonna say anything particular about it, At the end of the day, A is going to be in a certain state because you measured it. We got to project it somewhere. And we're going to look at all those states that A can end up in due to some measurement, which we haven't specified. I mean, the difference is that, of course, you know, to make a measurement is to specify an axis. And so then the spin could end up, you know, either spin up along that axis or spin down. We're not sort of considering that here. We're just sort of leaving open the question of like what measurement we did. We're just saying, well, like a measurement happened and A gets projected in a certain state. Maybe it's this purple one here. And the question is, because of the entanglement, what happens to B? And the idea is that B ends up in a state where it's like wherever the purple dot is over here, like there or something. Now there's a couple caveats.
But isn't B the same direction but opposite spin, or not necessarily?
Not necessarily.
So like for a graviton, for example, which could be spin 2, you could have 5 states, actually 4. So
yeah. So
what maps A to B could be.
So in that case,
the always a one-to-one mapping.
Yeah, the problem is that like for higher spin particles, it's like the state space isn't just a sphere, and so it's like a little bit more complicated. This whole
so this has got to be the half spin or spin 1.
Spin half, yeah.
Spin half or spin 1. Spin 1 for a photon.
Oh yeah, sure. Okay. Fine.
But so for a graviton, it would have to be a higher dimensional sphere.
Yeah.
Okay.
Basically. Now there's some tricks that allow you to work with the 2 sphere instead of just higher dimensional spheres, but that would take us too far. Okay, so.
But Matt, how does this random, not random, but what looks like a spherical distribution of states, how did that map into a straight line, for example?
Great question. So before, when I made this state, here I'll like walk you through the program a little bit. So what it does is, these are some functions that do the stereographic projection, basically. Then we make a state. Here we go through, you know, a bunch of points chosen on the sphere. For each of those points, we form the projector, and we tensor it so the projector just acts on A. And then, you know, we just go through all the points and then project A into that state, and then look at the partial state of B, and then look at the expectation value XYZ of the B state, and whatever. Now, to answer your question, we can choose. Before I just had a random state of 2 qubits. Could be separable, could be entangled. But now let's impose, we want a separable state. What do the separable states look like? They look like that. Now, why does that make sense? Well, the particles are not entangled. They're separable, which kind of means like they don't have anything to do with each other. So like B is in the state, and it's like no matter what point I measure A to B in, B is still in that state, separable. And so it's like actually a degenerate ellipsoid. It's just a line.
And then if they were partially entangled, it would be some other shape.
If they're partially entangled, it would be, in general, an ellipsoid.
Right. Okay.
So we'll do that again. Yeah, we get this sort of ellipsoid.
And of course, a straight line is a special case of an ellipse.
Yeah, exactly.
Okay.
But now let's do like a maximally entangled state. So like here's
like, could I just for clarity for myself, ask about that when you had them all lined up when they were separable and on not entangled?
Yeah, look back to that.
Because maybe that's an opportunity to clear up something that, for me at least, because
okay,
that sounds like the simplest case we're going to consider. So in this case, in the red sphere, the significance, I mean, it's like the red sphere is particle B, it's unrelated to particle A. Mm-hmm. So given that, what is the correspondence between the colors of the points in the red sphere with the colors of the points in the blue sphere?
Yeah, great question. So the depth of the point in this red sphere has to do with the probability of the outcome for A. Why is that? Because it's like we have our 2-qubit state, and then we say, oh, A ended up in such and such a state. And then we project. But when you project things, it's gonna lose information. Like when you project something, you're just sort of saying like you know, the classic example of like a projection in 2D is like, you know, here's a point. And it's like, I want to do a projection. Like, let's project it to the x-axis, right? Like, we got this arrow here. We could say, project it to the x-axis. That's the projection onto the x-axis. And so we actually lose information.
So I just, maybe there must be some, they can't be totally unrelated, the two particles, for there to have any meaning for this. Color of fuchsia in one, you know, being the same meaning as the color fuchsia in the other.
Well, so what I'm trying to say is that when we project each of the states, A, into each of its states, that will happen with a certain probability. Like A over here, if we end up in this blue state, you know, like A, it would be very unlikely for A to end up, you know, here, say. Why? Because its spin axis is like pointed in the opposite direction. So then when we project this entangled state into each of these states for A, then, you know, we've actually fucked up the normalization of our state. And so the
what does the state look like to begin with, where it's not entangled? If it's not entangled, then there's nothing going on.
Yeah.
You can measure one particle and do whatever you like with the other one.
Right. So this guy, like the fact that these colors are arranged on this line, in some sense, has nothing to do with B. It has everything to do with A.
Oh, this is just like a color scale, kind of.
Well, what it's saying is that
you got the fuchsia is like really low probability. That's why it's in the other direction from the pointing, race pointing.
Yeah. So I mean, the colors again are fixed. Like the colors don't represent probability or energy or anything. They're just, you know, helping you to remember which point on A sphere corresponds to which point on B sphere. But you see, yeah, like this purple guy in the middle, the reason the purple guy is like in the center there is because like that's opposite to this guy's spin axis. Whereas like A is very likely to end up in one of these black states. And so then we see here, like all the black states are there. So we're gonna come back to this point about like, there's like an interpretive issue here that we're about to come to.
But Matt, if A and B are not entangled, then
yeah,
where B doesn't, you know, B is completely independent of A. You take a measurement of A,
so
make a prediction.
So what do you do, like when you make a quantum measurement, like when you represent that mathematically, like you have a 2-qubit state, maybe it's entangled. So then you like say, you measure A to be in a certain state. So you project A into that state. But then what do you have to do afterwards? You have to normalize the state. Because the norm of the state after you do the projection is going to be proportional to the probability that you end up in that state. So it's like if we have two entangled particles and we project one, then, you know, after the projection, the two end up in a separable state, except the overall normalization of the state has been fucked up. And so we have to normalize it. So we just, in general, when you do this, it's like you project the state, but, you know, weight it by the probability. So you like fix the normalization.
So are you saying that the situation is that initially they are entangled, and then you measure one, and you're considering cases where post-measurement they're no longer entangled, and,
yes.
and that one is still affected because of this normalization?
Matt, can I make a stab at, tell me if I'm right here.
Okay.
So imagine I have particle A in the superposition of two states. And I have particle B in some particular state, and I take the inner the outer product of that. So that just says particle A is in either this direction or that direction, and particle B is definitely in this particular direction.
Mm-hmm.
And particle A maybe had a 70% chance of being in one direction and a 30% chance of being in the other direction.
Sure.
So then I do a collapse. I do a measurement, and it ends up that particle A ends up being in the direction that it had a 30% chance of being in.
Mm-hmm.
But particle B is always going to be in that other direction. Now, so what these pictures show is the blue picture shows which of those two directions I ended up finding particle A in. But particle B was always in that one direction. That's why it's on that line. But the different colors tell you which one it lined up in. So the red one, if it lined up with the red, if the 30% one was red in the blue world, then it showed as a red dot in the pink world. And the depth in the pink world would say, oh, and that happens 30% of the time. Yeah, it happens 30% of the time, but the other 70% of the time, you still get the same direction.
Yeah, that's basically right. Yeah, you got it.
Yeah. Thank you, by the way, that clarifies things for me.
So yeah, I have another, oh, actually, wait, yeah. So now I want to show, so what happens now if these guys are actually maximally entangled? In the cup state, like the state we were using before, the simple maximally entangled state. And it's a sphere. So it's like, we have these two degenerate cases, like when the qubits are, like separable, we get a degenerate ellipsoid that's a line. When the qubits are maximally entangled, we get kind of like a degenerate ellipsoid, which is like a sphere. And then when things are in the middle, we get just like some general ellipsoid. The reason the sphere is shrunk is because, this is like two entangled qubits. And so, they're each in like the maximally mixed state. It's like partial states. And so the probability of being in any one of these is all just like a half. And so it's a half-size sphere. But now I want to note, though, that this is an important point. Like, you might have thought, well, if like I have two maximally, entangled particles, maybe like it's the same exact sphere on both sides. And it's kind of true, except it's actually flipped upside down. And by the way, completely ignore, oh, that's like a little error. Completely ignore these arrows. They should be 0. There's a bug in the program. Ignore that. These arrows shouldn't be there.
It's 0 because you're saying it's not pointing in any direction?
Yeah, in a maximally entangled state, the two qubits are in the maximally mixed state, which represents the point in the center of the sphere.
You're
So
saying
it's equally probable to be anywhere on the sphere.
You're saying the total angular momentum is 0?
No.
You're saying that the expected angular momentum has no direction.
Yeah. Okay, yeah, sorry. Yes, that's right. So what's interesting about this is like these two spheres are basically the same, except one, they're like flipped in the X direction. So up here we have, green, but then like down here we have green, right?
Because if you measure spin up for A, then B has to be spin down.
Yeah, except here's the thing. It's like, what state are we working with? We're working with this state, 0, 0 plus 1, 1. So that's the maximally entangled state in the Z basis. In other words, if I measure Z, the one particle to be spin down along the Z direction, the other one's gonna be spin down along the Z direction. If I meant spin one up for the spin up for the one guy along the Z basis, then spin up for the other guy.
Right. This is not the Bell state of tradition.
No, it is. Yeah, it is the Bell state.
Well, it's not a traditional EPR version of the Bohm. Normally they have one up, one down, and then the other one is one down, one up.
Oh yeah, we could do that one too. So notice this. So in terms of like this visualization, like horizontal is X. Was that even true? Well, basically what I want to point out is that, yeah, that's right, sorry. So horizontal is X, vertical is Y, and going into the screen is Z, okay? So if we did a Z measurement, that would be like maybe we measure this particle to be in this like little blue state here. Then we see that there's a perfect correlation. This guy, if we measure this guy along the Z axis, like right there, then this guy will always be in exactly the same state. And that's actually true for every state on the equator. But you see that if we did say like a measurement along the Y direction, then the spins would be anti-correlated, right? Green up here, but green down here. So this is worth mentioning. It's like we have a maximally entangled state, but that doesn't say enough, right? It's maximally entangled in the Z basis. In other words, if we make a Z measurement on A and B, then we get a perfect correlation. But for example, if we measure Y in the Y basis, then we're going to get an anti-correlation.
So that's what you wrote. You wrote that state 1100 in the Z basis.
Yes, yes, I did.
Wait, Matt, is this for a real particle?
Yeah.
I mean, if you measure if two particles are maximally entangled and you measure one of them in any direction, then the other one, if it's maximally entangled, has to be.
It's not true.
Along the same axis, it has to be in the opposite direction.
Axis, yeah.
Along the same axis, sure. If you measure X, then you don't know what Y and Z are.
No, Michael.
You can see from this image that you just get, somewhere, you actually get somewhere on the sphere that's been Y flipped.
Michael, you're looking at a different state. He's looking at 1100. You're talking about 1001.
We could do that too. Why not? Let's do that.
But does that correspond to real particles?
Yeah.
1100?
1100. Well, wait. What state did we want? 1100 is not a maximally entangled state.
No, 11 plus 00 is the
Plus
one.
00.
Oh yeah, that's one we're using. Yeah.
But is that can that correspond to a real particle?
That one doesn't conserve. Doesn't conserve.
Oh, you want to use the anti-symmetric.
The anti one conserves spin. That's why it's more commonly used.
Right. So let's do that one. Yes. Fair point. Why not? So, yeah, there it is. And we see that it's been, flipped along the x-axis. And also the x-axis and the y-axis or whatever, I guess. See, because you got green down here, green up here, but then also red over here, red over here.
That's right. Because that's a symmetric state.
Yeah, right. So they're always pointed opposite to each other. Exactly.
And along the z-axis too.
Well, actually, interestingly, for this one, it doesn't matter what, in any direction, they're going to be anti-correlated.
Right.
Yeah.
So getting back to my question, 11 plus 00, does that correspond to a real particle?
Yeah. Yes.
What particle?
Oh, it's not,
It's not a particle. It's just not an isolated system because angular momentum has got to be conserved. So it's in a state, and then you go into a state where it's 1-1, then you've gone from 0 total angular momentum to 2. So something else has had to pick up the angular momentum. In the other case, Bohm case, when you have 1, 0, 0, 1, you're in a zero state, you're in a zero angle momentum state no matter what.
Oh, okay.
Yeah, this was a good point. Yes, yeah, thank you guys for bringing that up. Okay, so returning to the main thread here. So when A and B are separable, this ellipsoid reduces down to just B's spin axis. In other words, no matter what state A ends up in, B ends up in the same state. There's no correlation between them. When A and B are generally entangled, for each state that A ends up in, B's spin axis gets steered to a corresponding location. But of course, yeah, remember there's still quantum uncertainty, so that even if its spin axis has been moved a little bit, this still represents a quantum mechanical system, and so the ultimate outcomes that you get are still statistical. You have yet to determine what axis you're going to be measuring B along, and the answer B gives will be probabilistic. But what the ellipsoid shows you is that because of the entanglement, A can control the variation of A around its, A can control the variation of B around its spin axis. And the degree to which it can do that is represented by the fatness of the ellipsoid. So the fatter the ellipsoid, the more entangled. And the reason I brought up one of the reasons I brought up the maximally entangled state that I did before, where the two spheres are basically just flipped along the y-axis, is it's very reminiscent of our two coordinate charts on the Riemann sphere. It's as if here's a projection from the North Pole, here's a projection from the South Pole. Like we have two coordinates from so you could think about like in this maximally entangled state, you could be like, well, are we even really talking about two spheres or just two coordinate charts for the same sphere? Kind of a metaphor, but maybe not. Okay. So again, yeah, we've been sort of wrestling with the meaning of this ellipsoid and the significance of the depth of the point in B sphere. And we've said that it corresponds to the probability of the outcome for A, because when we project A, we don't normalize the state. And when we do a projection, we're throwing out information. Now, because we only have two qubits, when we do a measurement on either one of them, they're both going to end up in pure states afterwards. So really, we should push all the states out to the surface of the sphere. That would make some sense. I mean, we'd lose our ellipsoid, but what would we get? And in some ways, you guys already know the answer. So now I just normalize those points. I just project each of those points out. And because we were working with an ellipsoid, what you get is a Mobius transformed version of A's sphere. So actually the relationship between A's sphere and B's sphere is a Mobius transformation. It makes sense because an ellipsoid, you project it outwards. I mean, what do you get? It's sort of translated within the sphere in a certain way. And it's also boosted. And you can think about the boost as just you're squishing a sphere into an ellipsoid. Now, again, the color, we got to keep a couple things straight, right? Here, the color means what state, do we start off for A, right? So that this green state for A ends up being over here, this green state for B. So, that's how we're using color in this particular visualization. In contrast to, okay, so that's kind of interesting. Because it means if we follow this analogy between, relativistic momentum sphere and quantum angular momentum sphere, then it's as if nature herself has given us a cool metaphor which is that separable states are like states that are maximally boosted relative to each other. In other words, states that are moving at the speed of light relative to each other. And maximally entangled states are like particles that are at rest. And it's kind of a cool metaphor because, you know, operationally, like that's kind of how it is, you know, to say that particles are at rest is, you know, they're in like an inertial frame. They got, you know, it's like they're somehow correlated. They agree about stuff. They agree about, you know, perhaps the XYZ directions, for example. And so because of the fact that all this kind of basically susses out to being a Lorentz transformation, we can actually calculate this ellipsoid in an easier way. Before we, you know, took a bunch of points on the sphere, got the projector, project the entangled state, looked at the partial state of B, da, da, da. But we can actually use the Pauli basis that we used, you know, last time to calculate this in like kind of a more awesome way. So for example, if we have our 2-qubit state, we can form its density matrix by taking the outer product with itself. And we get a 4x4 density matrix. This is a density matrix that represents the pure state of 2 qubits, each of which is in, you know, possibly a mixed state. Now that's a 4x4 Hermitian matrix because density matrices are Hermitian. And so we can expand it in the Pauli basis, where we take you know, we go through, we have I, X, Y, and Z, and we take all the, like the product of them, you know, each of these operators, you know, this means like Pauli X tensored with Pauli Z. And then we can take our matrix and then just take like the inner product of that matrix with each of these 16 guys in turn. And because the density matrix is Hermitian, this resulting matrix will be real valued. And you notice that the first row and the first column are just our 4 vectors representing the expected spin axis of qubit A and qubit B. And somehow the ellipsoid itself must be encoded in this little 3x3 block here, the cross correlations. And then we can go in reverse. Suppose we have like our 16 numbers and then, you know, we just weight each of these 16 operators by those numbers and recover the original density matrix we started out with. Now here's the cool thing. Suppose we have a qubit state psi that we want to use as our projector. So what we've been doing so far is we had like the state of A and B. We multiply it by the projector onto psi, tensored with the identity, and then we take the partial trace over A to get the partial state of B. And then we expand that little density matrix as a 4 vector. And that's what we've been doing. But it actually, there's like a much more transparent way to do it in like almost completely relativistic language. Look at this. Instead, like let's form the 4 vector of our state psi that we're going to use as our projector. And then it suffices to simply multiply that state by this matrix on the left to get the state that B is steered to. And then we can do the same thing. Like suppose it was B that ended up in this state and we're wondering, where does A get steered to? And then we just multiply this little guy from the right and then we get the state that A is steered to. How cool is that? And this, you know, sort of this, you could think of this as like a 2-index Lorentz tensor. And it changes under Lorentz transformations on A and B separately, kind of in the obvious way here, where you have the density matrix and you have like some Lorentz transformation acting on A, and then you take for one on B, like some Lorentz transformation, the transpose of it. And so, you know, this does it. Like this takes a qubit state, turns it into a 4 vector. This takes a 4 vector to a Hermitian matrix. This takes our 4x4 density matrix corresponding to the state of the 2 qubits together and forms that Lorentz tensor. Note, secret factor of 2. There's always these factors of like 1/2 everywhere. Watch out. And then this goes from the 4x4, you know, whatever, back to the original density matrix. And we can see here that, you know, the 2 methods give us precisely the same answer. So, you know, here's some random state we start with. Here's the point that we're going to project onto. We take its outer product, that's the projector. It acts only on A. Then we project the state and then look at the partial state of B and then turn that into a 4 vector. But we could adjust, turn the state we want to project into a 4 vector, take the overall density matrix of the 2 qubits and turn that into our 4x4 real valued matrix, and then just multiply the 4 vector of A, the state that we want to project A into, by that 4x4 guy, and we see that it's literally doing the same thing. Okay, so now I have like a cooler, more animated visualization of this, which it's faster because that's a faster way of doing it actually. Whoa. So good. Entanglement ellipsoid. Okay, nice. So like, evolve. .05, whatever. Sorry, little prep. Okay. Aha. So it's like, let's like, evolve this state in various ways in real time and see how the ellipsoid changes. Okay, so this would be like more interactive. So the first question is, suppose we do an X rotation of A. What happens? And we see that the image of B rotates, which totally makes sense because like this guy is rotating. We see his little expected value there, his little expected spin axis is rotating around the X direction, and correspondingly, this whole sphere is getting rotated, so obviously these are going to end up in rotated locations. So that's if we rotate spin A. But what if we rotate spin B around the x-axis? Here, it's actually moving the entire sphere around as, the spin axis rotates around the x direction. It remains in the center of the sphere. It's actually kind of difficult to see just because of the symmetries of this particular random state. Let's do another one. Yeah, again, that's not that obvious.
Can you decrease the number of points that you use that might be easier to see?
Wait, say that again, Marty?
Decrease the number, you don't have my microphone. Decrease the number of points and it'll be easier to see.
Oh, that's true. Well, actually, this is a good example, actually. I just needed like a fatter, like a thinner ellipsoid that was like oriented in a different direction. So like, let's do like a Z rotation. All right, that makes more sense, you see? So we're Z rotating, just B, and we see like the whole ellipsoid, tracks the motion of the spin axis as we're rotating it. But then that's if we rotate B around the Z axis, but like instead let's rotate A, and that rotates the points on this ellipsoid, like leaving the ellipsoid itself fixed. We could even like let's just evolve both of them under some random Hamiltonian. And like, as we watch that happen, the entanglement's gonna change, an interaction. These two qubits are evolving together. They're getting like more entangled, less entangled. And you can just read it off from this. Like whenever this ellipsoid gets really fat, it's like, oh, that's maximally entangled. Whenever it's getting like super thin, it's like a pretty separable state. So you can just read off like exactly how these two qubits are entangled by just like watching this thing do its thing. And like, this is kind of the point, which is that like, you know, entanglement is a word. There's a metaphor that comes along with that word, like entanglement, like something, strings, things are tangled, whatever. Okay, entanglement is a linear map between all of the states of system A to states of system B. That's what entanglement is. Everything else is just a metaphor.
Is this visualization, does it have a name, this way of looking at things?
Hell yeah. So somewhere buried in here, there's a little reference. It's called, yeah, there's a nice paper called Quantum Steering Ellipsoids from a couple of years ago. And they go into the whole thing. You know, so you can look at this paper and yeah, behold, ellipsoids, etc. And, you know, they actually go into the different, you know, like degenerate cases, exactly, you know, whatever.
And is the goal to flesh out a new visualization scheme and like a representation, or is there like a after doing that a discovery or some additional insight that, or is this like a convenient tool?
Well, look at this cool theorem here. A 2-qubit state is separable if and only if its steering ellipsoid fits inside a tetrahedron that fits in the sphere.
Sure. Well, the whole thing's very cool, but you know, whether or not everything in this has a one-to-one correspondence, it's something already known, which is not a problem for me.
Yeah, I mean,
a valuable thing in its own.
Yeah, I don't know exactly. Yeah, did people know about this earlier? Like, is this? Yeah, it's a good question. I don't know. Yeah, how profound is this? We'll see. So, okay, wait, there was one more thing I wanted to say about that. Where'd it go? Code. Okay, so one thing we can do is like, let's show both, you know, A and B. Okay, so it's like we've done it twice here. You see what I mean? It's like before we were just looking at like all the A states and then like where A gets, then where B gets steered to because of where A ends up in. But like now let's do the same thing. Like here you see, here are all of B's states and where A gets steered to. And, you know, we can let them evolve under some random Hamiltonian and their entanglement is increasing, decreasing, all sorts of things. And you can see its dynamics results in basically the evolution of these 2 ellipsoids, which are basically like the image of the guy's sphere that's been, what can you say, boosted and rotated. Really, at some level, nothing more than that. And then finally, let's normalize our states. And then like that's sort of what we're going to turn to kind of close it out. Let us normalize. Yeah, cool, nice, look at that. You know, it's just the ellipsoid from before, but now it's on the surface of the sphere. Okay, but now here's the point that I want to make about that. In this particular visualization, I've used color to represent one thing and one thing only. And it is like which state of A corresponds to which state of B. Right? So it's like the fact that this is green over here and this is green over here means like those are the ones that are related. But like, let's throw that out the window. Forget about that for a second. And think about the color like we were thinking about the color before when we did just our Mobius transform sphere. Now, when we measure our qubit, they're both gonna end up in separable states, meaning that they're both gonna end up in rank 1 states. So really, they should be on the surface of the sphere, like I put here. But now the probability becomes the color. So I didn't do a visualization of that. But imagine it's like we have our sphere and we have like an ellipsoid. and then we do this. We like project the ellipsoid out to the surface of the sphere. But like, let's keep track of the color now and say that the color, we're going to represent the probability as the color. Because, and that makes sense because, you know, morally speaking, these really shouldn't live in the center or like in the interior of the sphere. They only live in the interior of the sphere because it has to do with the probability of the outcome for A. But they're rank 1 states. So they really live on the surface of the sphere, but they just have a different normalization. Again, normalization has to do with the probability of the outcome. So, you know, what we can say is that, like, again, ignore these colors. Imagine a different conception of color where we're taking our, like, say, all the points are the same color. They're like arranged in an ellipsoid, and then we're projecting those points out to the surface of the sphere. And based on the depth they were in, they're gonna be like, if they were like really deep in there, they're gonna be like red. And if they were like really close to the surface, they're gonna be like blue. So why do I, so here's why I emphasize that. Because it's like kind of a cool thing. So like, you know, there's a classic discussion in like like probability theory, which is like, what is probability? Some people say probabilities are all grounded in frequencies. Like the frequency of an occurrence, like, oh, I do this thing over and over again, and half the time this happens, and half the time that happens. And then other people are like, well, you know, but maybe probabilities represent like the strength with which I believe something. So I would assign something a higher probability. If I had good reason to believe it was more likely to be true, and maybe that makes more sense because after all, it's like, you know, we can assign a probability to like, you know, the coronavirus happening, even if that is a unique event, right? So that's usually like the knockdown argument. Like probabilities can't really be frequencies because we can assign, you know, rational probabilities that make sense, even if the event only happens once, I guess, because our beliefs are interdependent on each other. But here, I just have to say, I mean, in some ways, this is like some wordplay in a way, but there's like, you know, really exploring this sort of metaphor that nature has given us between the classical relativistic sphere and the quantum angular momentum sphere. So in the relativistic momentum picture, the color of a point on the sphere is its energy, which for a photon is proportional to its frequency, okay? And again, frequency of what? The photon is a particle that corkscrews, and the frequency is how quickly it's winding around in the plane, which is orthogonal to its motion. Because after all, a photon always moves at the speed of light. So if it's vibrating in any way, it has to be vibrating in a plane orthogonal to its motion. In contrast, in the quantum spin picture, we have 2 qubits, and for each state of A, we see where B is steered to, a point in the sphere. Its direction picks out a pure state that B must be in, and its length is proportional to the probability of the corresponding outcome for A, as we've been saying. This makes an ellipsoid, but these are all rank 1 states. They really should be normalized, pushing them out to the surface of the sphere, giving a Mobius transform version of the sphere. And we're going to remember the norm now as the color. So we get a Mobius transform version of A sphere, conformally transformed, red-blue shifted. And here, the meaning of the color isn't the frequency of the photon, like the frequency of the light. The meaning of the color is the probability that if you measure A and B to be, sorry, if you prepare A and B to be in this particular entangled state, and A is measured to be spinning around this axis, that you'll find B to be spinning around that axis. And the color of that point on B sphere isn't the frequency of an oscillating classical photon, but the frequency with which, if you do this experiment again and again and again, you're going to observe that outcome, that B is spinning up along the axis picked out by that point relative to A. And so it's kind of a hilarious twist on what the fuck we mean by a frequency, you know, like a color or like the frequency with which we obtain a certain quantum state given a preparation in an experiment. And so, you know, it kind of is a deep analogy, I would say. And here's just a random sidebar. Like this is like a little bit, like I don't, this is like not like something that I read in the paper. I just was thinking about this. You know, it's like, you know, in classical relativity, like in special relativity, like there's no cap on energy. Like energy is kind of like whatever, it could just be anything. But here, you know, because in the quantum picture, like because of the fact that probabilities sum to 1, it's like there's a maximum energy for the photons. And it's just kind of ironic because normally it would take considering gravity to put a cap on energy, in the sense that we would say like, well, if a photon had like too high of an energy, it just like would collapse into a black hole. And so you'd like never see it to begin with. And then people worry about like, well, how does quantum mechanics, like how can it continue to preserve probability even though things like apparently disappear behind horizons? But there's a funny irony here, which is that, you know, in the first picture, gravity makes you suppose a maximum energy and then you worry about probability sum to 1. But in our spin picture, we impose that probability sum to 1. And metaphorically, that's kind of the same as supposing there's a maximum energy. But yeah, so anyway, that's just a sidebar. But yeah, the punchline is this. 2 senses of the word frequency. One being the frequency of a classical relativistic photon. In other words, its color. There's another sense of frequency. The frequency with which I get a certain outcome to a quantum experiment. And we see here that the metaphor is actually perfect. We can describe the quantum spin picture, the probabilities as literally being colors on the sphere in exactly the same way. But of course, they're not colors you see. But that's the point, right? Because we do in fact see the celestial sphere. We see momentum. We see photons coming in with directions, with colors. And therefore, we can also see the quantum space of a spin particle because of this analogy.
Are the two frequency? It's like the concept of frequency appears on both sides, but can you say more than that? Is it like definitely not a coincidence, or just sort of because it's easy to find the probability? I mean, like the probability of finding that photon. Where, like, I don't know, it still could be a one-off. Is it meaningful really, or is it just sort of maybe meaningful?
I would say I think it's meaningful. It may not mean everything you think it means or whatever, but I would say this, that again, on the one side of the equation, we have classical relativity. And so, you know, frequency doesn't mean, oh, like the frequency of an outcome, some quantum experiment where the answer is random, etc. Frequency is just like literally like something's oscillating, you know, at a certain frequency.
Yeah, I guess that's kind of what motivates my question, is that like what is happening with, you know, per unit of time is, or per unit of what, you know, the number of events per whatever. The two different kinds of.
Or sampling event. So one is how often it comes back to the same state, and the other is how often you get the same result.
Yeah, exactly.
Right.
So it's
but
kind
from
of
one, you wouldn't infer the other necessarily. Like the energy of a hypothetical entangled particle is not in this way directly. You know, you can't use that to predict its probability in this.
Yeah. So yeah, like we, you know, in real life, you know, if we wanted to really do, you know, the quantum relativistic picture of photons in the celestial sphere, we got to bring in a whole lot more machinery. We got to work with quantum field theory. We have to work with infinite dimensional unitary representations of SL2C. You know, it's a whole project. But to understand this analogy, we don't need all that. We can just work with these non-unitary representations of SL2C that allow us to talk about like classical special relativity, and then the you know, space of quantum particles on the other hand, quantum spins. So yeah, so then I just was going to make a sort of general philosophical comment about like relativity. Maybe see, like, you know, what can we learn from this analogy? Like, we're used to relativity involving relations like orientation and velocity. Like, those are the classic ones. We're always saying things like velocity has no absolute meaning. You know, there's only relative velocity. And we write down these numbers representing an orientation or velocity relative to some reference frame. And we can see that like quantum entanglement is actually just sort of a special case of this. Because for two entangled qubits, we can literally consider their entanglement to consist in two Lorentz transformations, one from A sphere to B's and one from B sphere to A, as if their entanglement consisted in nothing more than them being rotated and boosted relative to each other, kind of. I mean, remember, it's like a double-sided Lorentz transformation, but of course, for the qubit, we're talking about its spin, you know, its quantum spin, not its classical relativistic momentum. And so, like, the philosophy that here's how I interpret relativity theory, per se. In a relativistic universe, you can't view the universe as a big container full of stuff. The old conception was like, you got space, you got time, got this container, there's some stuff in it, and they're put into relationship by space and time. In contrast, in a relativistic universe, we have to regard it as that like things themselves maintain their individual relationships. And space and time are something that comes atop that, comes from that, but isn't built in. And so consider that, like, to make these visualizations at all, and this goes back, someone made a comment about this. I sort of had to insert myself in a certain way. What I mean is that from the start, in order to write down these vectors and matrices, like to assign numbers to them, I had to fix for myself what I mean by the X, the Y, and the Z axes for both of the qubits. Mm-hmm. I could have made different choices. Like I could have been working a reference frame where like, oh, this one's rotated or this one's this. But once I've made that choice, it's like, well, relative to the axes that I've chosen, okay, qubit A is boosted or rotated, whatever, relative to the other one. And the point is that, you know, the qubits themselves have this relationship independent of me, independent of my representation. It's a relationship just between the two of them alone. Because what I mean is that the entanglement is independent of the choice of coordinates. It's like, what it's saying is that, like, if suppose you fix an XYZ frame for A and you fix an XYZ frame for B, then I can give you the numbers that like represent the map from states of A to states of B relative to that choice. But, you know, conversely, the relationship between the two does not depend on the choice of the XYZ frames. It's defined intrinsically between the qubits. In other words, it represents like the relative frame between them, like in their own terms. And so you could argue that there's two senses in which we've generalized the geometry of Minkowski space. On the first hand, we've interpreted the same mathematical objects in terms of quantum, probabilistic, angular momentum. But also you could say we've interpreted entanglement as a kind of private relativistic relationship between systems. What I mean is this. General relativity kind of forced us one step. Like now we can't just say like, all right, so Bob's going at this velocity and, I'm going at this velocity relative to Joe. And so Bob and Joe must be going at some velocity in the naive way. It's like add them up. And it's like, it doesn't work because general relativity says, as we move around, like the metric by which we measure space and time changes. But still, things kind of interact locally. Things just relate to what's around them. It's just that you have to remember, like, as you move things around space and time, you have to transform them in order to account for the effect of curvature. But really, I would argue that, what is quantum mechanics, but just the idea that things can be arbitrarily related to each other. It's like, I'm not saying you have to give up the idea that interactions are described locally. I mean, if anything, they definitely still are, as far as we know. But that relationships between things are defined intrinsically between the things and not relative to their local surroundings. So that, two qubits come together and then they go apart. And like, no matter what their local surroundings are thereafter, if they don't interact, they remember their entanglement, because that entanglement is like a relationship privately between the two of them. It can't be defined in terms of anything else except just the two. And now you could argue, well, couldn't you get the same effect in general relativity if you just let there be wormholes, right? Like, you could just imagine instead of, there's like a tiny wormhole connecting the two particles, no matter where they go. And just saying, kinda is, in a way, probably something like that's true. But of course, in the classical general relativity picture, is not probabilistic. And so any kind of wormhole picture is gonna have to be quantum, and heck, that's what we've been talking about. So then finally, just a word on just like generalizing these things to like not just 2 qubits. So for example, like what if you have n qubits? So then you wouldn't, if you had 3 qubits, you wouldn't just have like a 1-index Lorentz tensor, so that's like the 4-vector. The 2-index Lorentz tensor is like the 16, the 4x4 guy. Well, then if you had 3 qubits, you'd have like a 3-index Lorentz tensor. We would take the product of 3 copies of the Pauli's for our Hermitian basis. And just as before, we can Lorentz transform the individual indices, but now there's a kind of hierarchy. We have this big 3-index Lorentz tensor, and it will send 4 vectors to the 4x4 guys. Sorry, I wrote 16 by 16 there, it's wrong. 16 guys, 4x4. It sends basically states of the 1 to states of the other 2, and states of 2 to states of the other 1. So it always maps like one guy to the rest. If we have 3 guys and we want to determine like where the 3rd state is steered to, we have to determine the 2 states. And this is important because, for 3 particles, it gets kind of tricky because there are actually states where, one particle, like for 3 particles, there's states where, like the fucking, which one is it? The W state or whatever, I forget which one it's called. But where 3 particles, each one's entangled with the other 2, but they're not individually entangled. So the point is, we could represent our big quantum system, instead of using like a big tensor product of systems, we could view it as a series of maps between subsystems representing their dependency on each other. So it's like you could have some big tensor product and imagine like, transforming just this one part of it, taking partial traces and stuff. But you could do the same thing as just like having a bunch of systems and these linear maps that like map them to each other based on their entanglement. We can use Lorentz tensor to map states of A to states of B. Provided the multipartite case, we also determine any other states that B also depends on. And if we fill in all the indices in our Lorentz tensor, in other words, if we like determine, A is this and B is this, then what we get is a probability that, A ends up this way, B ends up this way. What's the probability that that happens? In short, entanglement encodes the dependencies between the outcomes of measurements on different systems, even as each system has the freedom to choose an outcome at random. And then, finally, it's like, what if we're not dealing with qubits? What if they have like different symmetries, whatever? And, it can work in any dimension, basically. So it's like if you're interested in SU3, right? That could be represented not as like a 4-vector, but as like an 8-dimensional real vector. You would use the Gelman matrices instead of the Pauli matrices. And then the entanglement between 2 SU3 states could be encoded in some 64 by 64, or is that right? No, 8, I made the same mistake before. It's 8 by 8, 64 coefficients. 8 by 8 2-index tensor. Apologies for that. Okay, so then the general point is this, and this is the conclusion. Entanglement is a linear transformation that assigns a state of system B for every state of system A. Imagine a state of B living above, mathematicians would say, fibered above every possible state of A and vice versa. And that's really what entanglement is, without using a metaphor, although we have gotten great, we've gotten a lot of mileage out of.
You said a linear transformation, but it's not conformal.
Conformal transformations are linear.
I mean, I'm saying, but I'm not saying it that conformal isn't linear, but this is not a conformal transformation. Is that right? Is that?
In the case of like the general, like we're not talking about qubits.
I don't see it preserving angles in these pictures.
Well, so yes, like they're not going to be conformal transformations, like if we're using like SU3 or like whatever. But no, these are conformal in the case that I visualized here.
Wow. guess it's hard to check that by eye.
You're right. Like what I really should have done is like, maybe I'll do this for next time. Put a like latitude and longitude markers on the one sphere and then transform those instead of the points. That might be easier to see.
Maybe put like little lines to make constellations out of them.
Yeah, that too. Yeah, that would be also helpful. Totally. I mean, one time I actually did, this is pretty funny. It's like I bought one of these spherical cameras. It's got two cameras pointed in opposite directions and it captures spherical video. And then I actually like processed it to do like Lorentz transforms on the video itself. You know, so you could do rotations and then also boosts and like whatever. And so, you know, there it's like not just, you know, connecting the stars in the constellation, but literally I could do your face, Marty. You could have, you know, image of Marty conformally transformed.
No, please don't.
Was that like one of those Google Map or Street View type? Like, what was the intended purpose for that camera? I doubt it was Lorentz viewing.
Oh.
What was the intended purpose? Yeah, fuck me. I don't know. I mean,
It's a neat photographer gimmick.
People use them for all sorts of things.
Oh, it's a gimmick.
Well, I mean, it's like, well, I would say, I mean, they're useful for like, okay, like if you're out in the wilderness and you want some video of that, you can stick it on your head and get like, you know, full panorama. I would say it's probably good for podcasts because it's like if you're sitting across from someone at a table, it captures like both of you.
Right. Yeah, so just
I don't know.
360 viewing.
And if you want to work with VR headsets, you can you basically record spherical video, so then someone can like use a VR headset and like just literally enter the scene that you just recorded. So that is pretty cool, I would say.
So did you hack like the software or the programs that sort of knit the individual videos together to create a perspective, or did you come up with your like decode the codec and come up with your own?
Yeah, what did I do? I don't remember. It was like a year or two ago. I forget. But yeah, I mean, ultimately it was like loaded up the video file in Python, looked at the individual pixels. The pixels have like a direction in 3D and a color, and then I Lorentz transformed them. And that was basically that.
That's cool.
So yeah, any questions or concerns, or thank you guys for letting me get through all that. Tale of Two Spheres.
Okay.
Well, I have a lot of questions, but I don't want to be the guy that keeps everyone
No.
dinner or whatever. So maybe I'll just email them to you or save it for the beginning of next time.
Sure. Yeah, hopefully we'll meet next week. You know, we can do stuff then.
I'm still on the introduction. Oh my.
Maybe just one thing I'll throw out. My, from what I followed, like this guy, Zellinger in Vienna, does, to my knowledge, the coolest experiments that sort of flesh out the weirdness of quantum mechanics. I haven't really been tracking it very recently, but do you have I mean, is there anything that you know of his that, because it seems like he's already kind of demonstrated that there's no hope left for an intuitive view of quantum mechanics. Like, because he even had these things where you measure one particle and like a, you know, I don't know, like a space-like separation, where there's no chance. Like somehow, not only are they at a distance, but like whatever. Yeah. Do you know of anything that sort of like forced him to go back on? I expected some of these results to really have an impact in the broader media, but he seems to not get that much attention.
I mean, from what I understand, among people in the know, like that lab or whatever is maybe the best in the world. And I think they mainly use photons. Don't quote me on that. And like, you know, are always doing these experiments, entanglement, little quantum teleportation from place to place. I mean, you know, the history of like the general acceptance of entanglement, as you know, you probably know, is like a rocky one, from, you know, it being identified as just a like sort of intrinsic feature of this mathematical formalism, you know, from the beginning. But then, you know, in the papers in the 30s, like the EPR paper, Einstein, Podolsky, and Rosen, they're arguing about like whether this actually is like a reason to not believe in quantum mechanics. And then it was probably in the 60s with Bell and others that, it became clear that like you could, just set up experiments that would like rule out the idea that there was some kind of prearranged hidden variable that underlies the correlations between the entanglement. And then that those experiments were finally performed by like Alain Aspect and others. I don't know if I'm pronouncing his name right, it's French, in the late 70s or early 80s, I think it's the early 80s. And then subsequent to that, yeah, it's like, it's been confirmed time and again. I mean, I think the Chinese, did it like teleport.
He had a particular one.
The satellite,
You're already familiar with the, where he had like, there's like one lab on an island. This is still Zellinger. And it's so cool. There was some guy, I believe it was a guy that, like this was his PhD thesis. He got like, this experiment. So I felt it was just cool to know about this, but he got to have that be his thesis. So cool. Anyway, where they're sending out these coupled photons. Basically, one's going into a distant lab, and another one's going into a nearby lab, and but in both cases, like you could choose which experiment you do. You either send it to a double slit, or you measure its spin, and whether or not it's been a while since I looked at this thing, but it's like you could choose one experiment. You can measure one thing before the choice. Like you can measure the one that goes into the nearby apparatus before they would have decided which experiment to do in the further one away. And the choice of which experiment affects like the kind of interference you should be getting. So it's like, and it still comes out consistent with quantum mechanics. Like, like somehow the first particle to be measured, it knew what choice was going to be made in the other lab and stayed within those states, those substates.
Yeah, it's all true. It's kind of amazing. I mean,
that's the craziest thing I know. And I was like,
of course, I mean, the caveat I think that anyone has to say when they tell this to somebody is that it's like similar to a discussion we had like in the previous meeting. It doesn't mean that any information can be transmitted from the future to the past per se, because the outcome that takes place in the future is random. And so the thing that, even if it's transmitted into the past or whatever, it's also random. And so it's only in retrospect that you can see that that there's this effect. I'll make a note of that. I can go into like
you're familiar with that paper?
Choice experiment, because it's a beautiful experiment. Yeah.
Right.
But like, I guess insofar as it relates to this stuff, I mean, you can see it's like, even though because of entanglement, if you measure A to be in a certain state, it steers B, nevertheless, there's still quantum uncertainty. Like that doesn't fix B's state at all. It just fixes its overall, expected, its average spin axis. But, you still have to choose what direction do you want to measure it in. And then
I just realized a question I've always wanted to know is, okay, so you can put a lot of information into a qubit. Okay, but then you have to take it out again and measure it.
Yeah.
And so you'd have to do like 1 million experiments in order to get it accurate enough.
Absolutely.
A billion or a trillion.
Yeah.
Yeah, so that's the problem, But okay, because I was wondering when you said, like try this out, try getting on the quantum computer. I was thinking of the needle in the haystack problem. Like it'd make a very nice hash. It's like a nice hash table. You can find anything, and this seemed like a good reason to use a quantum computer. But you can only get a certain degree of accuracy, and it's based on your analog to digital converter.
Yeah, basically. I mean, it's a funny twist on, everyone's worried about these days, like how do you get neural networks to explain what they do? Like how do you
forget that.
Like a black box? The problem is only magnified with quantum mechanics, because like even if you could, I mean, yeah, it's known that like you can speed up database searches like crazy with the quantum computer and all sorts of stuff. But of course, you can load lots of information in the quantum state, but it's not legible. You can't just read it out because you got to make a quantum measurement to extract information from a quantum state, and then it fucks up the state. So then you got to do the experiment again, like 10,000 times.
Right, yeah, but you can do it
then
fast.
you can nail it down.
That's the thing. You can do a lot of experiments fast.
Yeah, so like in all those quantum, computing libraries, it's like there's always a function that's like, do this circuit and run it like 10,000 times. Just, like get the average of all the outcomes. Totally.
No free lunch.
Yeah. I mean, I think that is like one of the hardest things to understand, like initially about quantum mechanics. That's like all of the stuff that we're familiar with, like, something's spinning around an axis. Yeah, things still spin around their axes, and we can determine what those axes are, but it represents a statistical average. And, and it gets at what I was saying before about frequency. It's like all these things are statements that, aren't necessarily just about a single quantum system, but like if you could make a potentially unlimited number of copies of that system, you can't make a copy of a quantum state, but if you could prepare identical copies, do the experiment a bunch of times, like then
you could do it in parallel, probably over the same fiber optic line.
Yeah, totally. Like no reason to do them sequentially. Totally.
Yeah. Interesting. Yeah, but then you might as well make a regular digital computer, that's in parallel.
Yeah, so like that's what, exactly. When people design this stuff, that's what they have to balance. It's like, I mean, for a classifier, that might not be too bad. It's just like you somehow load all this stuff in, and then the idea is like you just measure the qubit at the end, and if it's up, the picture's a cat, and if it's down, the picture's a dog. Like you could do it with one measurement in that way, in that case.
Oh well. Okay.
Did you play around with the now available, like from IBM, I think, and D-Wave had its.
Yeah.
You play with those libraries?
I have. The one that I played around with the most is Righetti's system. Although recently,
Righetti.
And then also recently IBM system. I highly recommend, like in one of the emails I sent out, and also I put it in like the links page on the site, and like we'll talk about this like soon enough. There's a great library, it's called like Pytket, Pytket. And it kind of like unifies all the interfaces to all of the currently available quantum computing services. So you can just sort of like create a circuit and then be like, all right, run that shit on IBM's, or run that on Righetti's, or run that on this one or this one or that one. And like, it's kind of cool, like it just works.
How do you, because I know that you get like free, runtime a little bit.
Yeah.
But it always seemed to me like within that, like I factor something into its primes, and then all right, there you go. I mean, but to sort of really feel like you're seeing the power of quantum computation, I think I have to like pay for, resources enough to like deal with an actually hard problem.
That's definitely true. I mean, I would say this, that like, okay, Righetti has a 28 qubit one. That's pretty cool.
Yeah.
And they give you $5,000 to play around with. And I think the 28 qubit costs $35 a minute to use. So
and it's a minute of runtime. So like if you run like a millisecond execution, then it.
You have to, so you reserve it in like blocks,
Okay.
which I think have to be at least 15 minutes long.
I see.
But yeah, I really recommend you guys check out, like this is sort of not related to the sphere thing or anything, but this really cool talk by Bob Coca, Quantum Natural Language Processing, and this really, really cool piece of software that they just released, which has some really excellent Python notebooks associated with it. And it's all about that this yanking equation thing that we've talked about in previous meetups, and provides like a unified framework for like working with these cool string diagrams and for then, you know, interpreting them in different ways and then like automatically like running them on, you know, Rigetti or IBM or whatever it is. So we'll talk more about this later on, but you know, there's a lot of cool stuff to play around with that. And they use internally this thing I mentioned, was it pi to ket? I have to say, I didn't realize this thing existed until kind of recently. So I was excited by it. Yeah, here, this thing. Cambridge Quantum Computing. So yeah, it's like they support Google Circ, IBM, you know, QIS Kit, PyZX, Project Q, Rigetti, AQT, Honeywell, Microsoft, QDK. Great, it's all in one place.
Awesome.
I love that.
What's the like the minimum number? So like the most qubits, like proper qubits, is 28 now. That you said that.
I think that's the biggest I've seen.
So you need like 50 to have some supremacy or something like that.
Yeah, right. Like Google claims supremacy, and I think they had like at least like at 50 or something like that. I forget the exact number.
Is Google, are they using something other than the? I know they bought a D-Wave system like a while ago.
Yeah, I
must
don't
be
know.
using something else because that seems like that's a very sloppy. D-Wave system is very noisy and limited.
Well, yes, like the D-Wave system is not. You don't program.
Not really that many entangled qubits.
Yeah, like you don't get a bunch of qubits and then like the ability to do like arbitrary transformation
operations
measurements. Instead, you're sort of like defining a Hamiltonian, and then they,
Yeah, it can like relax to the ground state.
Yeah. So it's like a different paradigm.
Yeah.
So technically, they have like a shit ton of qubits, but like they're not like controllable in the same way, and they're noisy. Yeah, you're totally right.
And so Google has. Did they use something else for the supremacy? They have their own different.
Yeah, and they don't put that one online, as far as I know.
Okay. Yeah. Right.
Yeah.
Thanks.
Mm-hmm. Yeah. Any other?
I mean, I could talk about this forever, so I won't try to do it. But
okay.
don't let it be that the answer has to be no. There are no more questions for us to get off this call, because if that's the case, we're not getting off.
It has been a while, I have to say.
I know.
Wow, 7 o'clock, crazy.
Yeah.
Wow.
Well, thanks very much for the whole thing.
Yeah.
Mm-hmm.
Yeah, we'll continue this. Hopefully we'll have another meeting next Sunday. And talk about some other cool stuff. If you guys have like any questions or concerns, definitely feel free to email me. And I really enjoy kind of like tailoring these things that I prepare to the stuff that you guys are interested in. So.
Yeah, this is a really good time of day. It doesn't interfere with other, webinars. Yeah.
Yeah, I like it. 4 o'clock.
Is there anybody else last question, anybody else like Arkani, Hamed, that you're sort of following, you go out of your way to look for?
Oh yeah. Well, I'll put up a link to
yeah, you can answer that offline.
Inner helicity variables, which are cool. And Arkani Hamed didn't come up with that as far as I know, but that's just, he's good at explaining it. I really like Bob Coca or whatever, that's how you pronounce his name, because and a lot of these guys at Oxford, they, think about the intersection of quantum mechanics and category theory, and, he's one of the people who worked on developing the diagram language that we worked with, like the last 2 meetings with these cups and caps and stuff. And we'll come back to talking more about that next time.
I know I missed a couple meetings ago, like Cohn Specker, you covered that, I believe.
Oh yeah, we could talk about that. We didn't talk about it directly, but.
Oh, okay, and then like what's his name, Conway's conclusions and what you think of those. That'd be interesting to chat about sometime.
Oh sure, yeah. Let's definitely talk about that. Yeah, Conway's free will theorem. Fascinating.
Yeah. You covered that once.
Yeah, we talked about it a couple years ago. Totally.
Yeah, that's when I discovered this meetup. I don't know if I was searching that term or what, but
Oh, sure.
I
Okay.
learned of that meeting. It was already like 15 minutes into it. And I'm like, oh, it was too late. I think I emailed you like, hey, could I join? But you were already off and running. So
Bless.
anyway.
Yeah, no,
Very
I
good
found that paper
choice of
inspiring.
topic.
Because yeah, I mean, it's the fact that a lot of this stuff is free or random that is precisely what allows a lot of things which you would think would be contradictions to not be contradictions. Like, it would seem like entanglement would let you transmit information faster than the speed of light, but it can't, because even though things are correlated, despite how far apart they are in space and time, what they agree about is something totally random that couldn't have been predicted beforehand. And so no information is being transmitted. I can't just like do like telepathy. Even if things can coordinate due to quantum entanglement, you know, the actual outcomes remain random.
But still, it's a phenomenon that sort of seems to live in a special place.
Say it again?
That it's a phenomenon, even if you can't, utilize it for like applications in such a way with information, it seems to sort of still compel you to think, how could it be possible, regardless of it being useful or not.
Yeah, well, and again, usefulness is not just, I mean, being able to have telepathy or to transmit information faster than the speed of light is not the only useful thing you can do. Because just for example, through just the correlations, you can, win the prisoner's dilemma. Like in game theory, you separate two prisoners and you're like, you see, they both betray each other, they're both fucked. If one betrays the other one and the other one tries to save the other one, then, the guy who was, who decided not to fuck over his friend gets fucked. And then, only if they both remain silent and not.
Yeah. So how do you keep your entangled particle from decohering as you commit the crime?
Yeah, exactly.
So that it's still entangled when you get caught.
So you bring up the point. Yeah, it's like you have to, to set up the quantum game, you have to have do a qubit.
No, I'm not trying to poke a hole in that. That's really cool, but it's just making it funny. Yeah.
So like in the world of quantum game theory, it's about there's lots of games that you can win that you just couldn't win classically, but things that are quantum entangled or have access to quantum entanglement can win with higher probabilities. So that's pretty useful, and especially when you think about the history of evolution as being having a lot to do with games.
Oh yeah.
It's kind of interesting. Evolutionary theory spent a lot of time trying to explain in classical terms how cooperation could arise from competition, as if cooperation was the thing that needed to be explained. But we live in a quantum world. Cooperation is kind of built in too.
I think something as basic as causality and time, we don't have that straight. So how can we understand anything else?
Right.
Yeah, totally. Yeah.
Also, why should it be that there's it's just about everything seems explainable and understandable, and that you have to wait for someone to do something really unusual and notice a really subtle consequence to discover that actually not everything can be understood in a satisfying way. And then you probe it and find that actually, if you zoom into any situation enough, it'll always look like that. That's I guess we get, if we couldn't explain most things, we wouldn't have a coherent society. These things have to live in the fringes.
Right. Yeah. All of these discussions take place, given the fact that we're highly evolved beings.
Yeah.
But who come from a specific history. So I mean, a lot of this stuff is why, like I was saying before, it's we can use, the relativistic sphere to visualize quantum entanglement between qubits. And that works because we actually, with our eyeballs, see the relativistic momentum sphere around us. It's just the photons with their colors or whatever. And that's something in our experience. We have eyeballs, we have brains, we think about things in a certain way. And so we can use those aspects of ourselves to understand this slightly more surprising thing about quantum entanglement. And like a lot of that is what this is. It's like, you know, whatever nature is, like whatever the right language is, at the end of the day, we have to find ways of displaying it to ourselves, given who we are in our history.
Yeah, I was.
We don't even know what that is, what our history is. We don't know what we are.
I wondered along those lines, like, you know, some people say like, well, what you're used to is what you feel like you understand, and so if we lived at the quantum level, that would seem normal, and if we moved it close to the speed of light, those effects would seem normal, or space-time would be bending if we were the size of planets. But I kind of wonder, like, in this universe, can you really have intelligent beings that are the size of a subatomic particle, or, you know, or like atoms, or the size of planets? You know, like, can conscious beings actually fulfill those hypothetical cases where you imagine nothing would seem weird then? You know, I wonder, it seems like maybe not.
Yeah, I wouldn't exclude the possibility. I mean, I think that, you know, one could imagine the universe as just like a fractal where you could just keep like zooming in or zooming out forever. And it doesn't exactly seem like that's totally true because, you know, gravity seems to suggest if you stick too much stuff in a place, they'll collapse into a black hole, so that there's like a kind of, you know, fundamental length scale. But at the same time, you know, and so that would mean that, like, you know, maybe like there wouldn't be enough room to like fit in all the information in a human body at like a smaller scale.
Right, yeah.
And like we're a lot of empty space too.
There's plenty of room at the bottom, but there's not unlimited space at the bottom.
Wait, say that again?
I said there's plenty of room at the bottom, but there's not unlimited room.
Yeah,
that's going to need a lot of room.
I think that's,
if such thing as continuum is real, then you need infinite storage to represent anything completely.
Oh yeah,
exactly.
Right, you need a computer the size of the Earth, whole universe.
Yeah, you need the universe to simulate the universe.
Yeah.
Paradox.
And it have to be itself.
Right.
Yeah,
like Stephen Wright, I have a map where the scale of length is 1 mile equals 1 mile, and it's the size of the country.
Yeah, totally.
But it's accurate.
Yeah. It took us all summer to make it. Yeah. Or to fold it. Actually, that's what he said. All summer to fold it.
Yeah.
Anyway.
Well, yeah.
Well, I think that's a good note to go out on. I gotta go. I have to like pee really bad and a little hungry, so I might leave it this. But
well,
great.
See you next weekend, and thanks again for your efforts and great job.
Yeah, thanks.
Really enjoyed it.
Thank you very much. Yeah.
Until next time.
Try to read your stuff.
See ya.
Yes.